Good morning and good afternoon, depending where you are, to everybody. Welcome to more one edition of our event, TYAN Virtual Meeting Workshop in Mathematics. It's a great pleasure to have you here. And today our topic is partial differential equations. So we will start with the opening, and I have the pleasure and honor to invite Professor Max Paoli, the TWAS program coordinator, to say some words. So please, Professor Max Paoli, the word is yours.
Okay, thank you so much. Well, it's with really great pleasure that I welcome all participants to this thematic workshop. I think it's incredibly important to support mathematics and research in mathematics because it's somehow an underrated science. And TWAS is very, very keen to increase the support in mathematics. The second reason is because this is an event organized or co-organized by TYAN, and it's really essential to help and support early career scientists worldwide, not only in developing countries, but worldwide, because they are the future. The third reason, although the third reason will not sound too good after I've been disconnected with an unstable connection, but the third reason is that these virtual meetings, which have become perhaps almost the norm, are incredibly useful because they're relatively easy to set up. Anyway, enjoy the meeting, and I wish you all the best.
Thank you very much, Professor Max Paoli, for these very nice words. And now I have the great honor and pleasure to introduce Professor Márcia Barbosa, the director of the Brazilian Academy of Science. So please, Professor Márcia Barbosa, the word is yours.
For the Brazilian Academy of Science, network is the core of making science. When I remember my own field, that's water, I remind you that water molecules, to have these wonderful properties that enables life, do something very particular. It makes hydrogen bonds. It's bond and then disconnect, bond again and disconnect all over the place. So we can see that the World Academy of Science, through this young affiliate networking, is doing something like this. It's connecting and connecting everywhere. And why this is so important? It's important because it brings diversity. It allows to put in science local diversity, regional diversity, people from all over the globe talking together and exchange ideas. And more than that, it also brings racial and gender diversity. So in the name of the Brazilian Academy of Science, I wish you a very fruitful meeting. But more than that, remember of networking and networking with diversity. Thank you.
Thank you very much, Márcia, for these very nice words. And now I have the pleasure and honor to introduce the president of the Brazilian Mathematical Society, Professor Paulo Piccioni.
Okay. Thank you very much, Jacqueline. It is a pleasure to be here representing the Brazilian Mathematical Society. When Jacqueline told me about this initiative of TWAS, the Young Affiliates Network of TWAS, I was extremely enthusiastic to support the initiative because it contains elements that are very important to the Brazilian Mathematical Society. In first place, mathematical excellence. That is, all the invited speakers to this series of networks are either young or senior researchers in the area that have a very good reputation worldwide. So this is the first very important point. But then there are other important points also, which is this series of workshop also has special attentions to gender balance and also geographic balance. And these are absolutely essential. We understand that these are essential points in the modern politics of science. So I was enthusiastic to offer the support of the Brazilian Mathematical Society, and we joined efforts with the TWAS, with the young affiliates, with the TWAS LACREP, the Latin American and the Caribbean Regional Department of the World Academy of Sciences, the Young Academy of Argentina, and the Brazilian Academy of Sciences and the Mexican Mathematical Society. We're very happy to collaborate with all these associations to bring together all these very important and interesting mathematics presentations. So my wish is that this initiative also continues along the time, so that more and more people can be brought to the attention of our community. And also I want to thank all the organizers and the speakers who have accepted to speak at this series of workshops. And with this, I just send you the greetings of the Brazilian Mathematical Society and give you my best wishes for a very fruitful meeting.
Thank you very much for your words. And now I have the pleasure to introduce Professor Maria José Pacífico, and she's member of the scientific committee of this event. So please, Professor Maria José Pacífico, the word is yours.
Many thanks for the invitation to be here. I think that most of you already told and represented quite well what this meeting, this series of meeting represents to the young people, and because they and all the mathematics developing in the world, I would say. And I am quite honored to be part of the scientific committee, and what is I would like to emphasize here is to say that the young people in the organizing committee for this series of meetings is really the strong part of this, like Jacqueline and Ferran, Franco, Hernan, and Eduardo Teixeira. They are really enthusiastic, and they are, how you say this, the strongest and enthusiastic, and just push everyone to happening and this kind of meetings. And we should really profit from this virtual meetings, and I hope that this will continue for a long time, not only because I think that this is I would say that I think that the only thing good that happened in this pandemic time, that we are profiting quite well from the virtual meetings along the world. And then it's a pleasure to be here, and I hope that everyone can profit from this meeting here. Thank you very much. Okay.
Thank you very much, Professor Maria José Pacífico, for these very nice words. And I would like to thank again all the participants in this opening. It's a great pleasure to have you all here. And now I pass the word to Professor Eduardo Teixeira, who is a member of the organizing committee, and he will moderate the event now. So please, Eduardo Teixeira, the word is yours.
Hi, everyone. Good morning, good afternoon. It is a great pleasure for me to be in this meeting. As was pointed out, I'm part of the organizing committee. And on behalf of the organizing committee, I thank you, all the members of the scientific committee, for helping us putting together this wonderful meeting. I should also say that we I'm extremely happy to be here today. But Professor Monica Musso was the one that was invited to be the moderator of this meeting. Quite unfortunately, she was not able to be here today, and I'm all very happy to be here covering for her. So with no further ado, let me introduce our first speaker. So as you know, today we're going to have 4 speakers. 2 speakers on the realm of parabolic and elliptic PDEs, and 2 speakers in the dispersive PDEs. And our first speaker is Marielle Saz. She received her PhD in 2005 from Stanford under Marcel. From 2005 to 2008, she held a postdoc position at the Max Planck Institute for Gravitational Physics. That's called also the Albert Einstein Institute. Currently, she's an associate professor at PUC Chile, and she has given many important contributions in elliptic and parabolic PDEs, geometric analysis, and more recently on non-local and fractional diffusion problems. And today she will deliver a talk on the mean curvature flow on graphs. Thank you so much, Marielle, for being here, and the floor is yours.
Thank you very much for the introduction and for the invitation. I'm very happy to be here. I'm very honored to be here. And I'm going to try to share my screen now. And the talk that I prepared today is more of an introductory talk to the topic. So only at the end, I'm going to talk a little bit about my own results, probably for the sake of time without proofs, but of course you can interrupt me and ask me more technical details. I thought about a broad audience that not necessarily are familiar with parabolic PDEs. So I'm gonna try to maybe go into too many details. So also tell me if I'm going too slow on this. Today I'm going to talk about the mean curvature flow graphs, and I chose the topic. This is a topic in geometric analysis, but this is very, very related to PDE theory, and that's why I chose this as a topic today. And I'm going to be emphasizing the aspects in PDE, or at least I will try to do that. But I need a brief geometric introduction, which for some of you, I guess, is going to be maybe too basic. So the problem that is behind all this is the problem of minimizing area, or considering the area functional in general, which is the functional that if you have a surface, you associate the area functional. And then if you try to minimize that, you get the following type of equation. The way you minimize usually is trying to consider a variation in any, for any function phi, and then you get a formula of this type. From that, you get a geometric quantity that is the mean curvature, and the mean curvature it's a geometric quantity that represents the average of the principal curvature. So if you're in a two-dimensional surface, this corresponds to the bigger and the smallest curvature, but in general, it's a family of corresponds to the eigenvalue of a matrix, and I'm gonna connect this with a PDE idea in a minute. So a remark here that is important, that is gonna be important in a few minutes more, is that all the variations that I'm considering, so all the variations are in the normal direction. And the reason for that is something that is known for a long time, that if you consider more general variations, I mean, if you allow the surface to be deformed also in the tangential direction, all the tangential components of the speed that you get can be understood as reparametrizations of the surface. And from the geometric point of view, a reparametrization is the same surface, and that's a freedom that you want to allow in these extrinsic geometric problems. In general, you're going to have some degree of freedom. That is the way you parametrize, and this reflects in a minute more in the PDE aspects of this problem that I want to talk about. Anyway, so Okay, if you study problem h equal to 0, this is a minimal surface problem. That is a problem that has been studied for a very, very long time. And from the PDE point of view, this has this can be seen as an elliptic problem, as a quasi-linear elliptic problem. In fact, it's something that is degenerate as well in some sense, because you have this freedom of parametrization, but it still falls into the framework of elliptic equations. Okay, so here I had a picture of what was the mean curvature. I guess I should have put the slides in a different order. Here what I was trying to show is what the principal curvatures are. The principal curvatures, as I said, if you look at all the curves that you're on a surface, the principal curvatures correspond to the biggest possible and the smallest possible. So in this picture, I was trying to show that, but maybe just to give an idea that there's something geometric behind this. But from the PDE point of view, maybe the important part is that this is the divergence of the normal vector. This can be computed as the divergence on the surface of the normal vector. And with the idea of the divergence, this maybe reinforces what I was saying before, that the normal vector is something that you compute in terms of the first derivative of the surface. And the divergence of that gives you a second order problem that, because of the structure, is of elliptic nature, although it has some degeneracies because of this freedom of reparametrization. And here's the example that I want to focus on today. That is the example of surfaces that are given by graphs of functions, so surfaces that can be written as x u of x. In that case, the area is computed in this form. And then when you compute the mean curvature, if you compute the variation now in a setting that is probably more familiar for PDE people that are not so familiar with geometry. So I know that many of you are also familiar with the geometric setting, but in case someone is not, if you think about this as E of U, and then you try to compute, sorry, I don't know how I did that. If you try to compute ddt of E of U plus T phi, the quantity that you're gonna arise with is this quantity here. So now it looks more like something that could be more familiar for someone that is coming from the PDE world, but not from the geometric world. And if you're looking at this equal to 0, you're gonna have something here that morally looks like a Laplacian equation, but you have a coefficient that depends on you as well. That is this gradient that you're seeing down there. And this is the type of problem that I'm gonna be trying to analyze today and trying to see what tells us from the PDE point of view and also from the geometric point of view. Okay, so this is exactly what I said. And I said this is an elliptic problem, and I'm gonna be talking today about the parabolic version of this problem. The parabolic version is usually called the mean curvature flow. And the mean curvature flow is something that has by now a long tradition. It has been extensively studied since the 80s mostly, but it's an older problem. It's something that is been in the field from the 60s probably, or even before, because it has some applications in material science. So actually, some of the things that I'm not going to talk about today, but that are related to this problem, come from an application that is the fact that in nature, many objects, when they minimize energy, what they're trying is to minimize surface area. So in the process of minimization, what they try to do is to minimize mean curvature, and the most efficient way of doing this is the mean curvature flow. So the mean curvature flow in the language of geometric PDE is usually referred as the gradient flow of the area functional, and this is just a fancy way of saying that this is, sorry, there's a bug here. That is the most efficient way of decreasing the area functional, and that just translates into the parabolic PDE that is associated to the elliptic problem that I tried to describe before. Okay, so here's the parabolic PDE that we're going to be looking at. Is something that looks like this. Here is the normal vector. As I said, somehow the normal directions are what really deform the surface. All the tangential velocities can be associated to reparametrizations of the surface, which from the geometric point of view is like you're not changing anything. So you're really only interested in the normal speed. But as you see, somehow I have the freedom of, or maybe the problem, that I can choose any tangential speed here. And this is gonna reflect in the PE somehow. Okay, so so first thing is, from the PE point of view, you want to you wonder if this is a well-posed problem. As I said, this is degenerated and it has some degree of freedom in the parameterization sense. And what you can show is that if you start with something that is smooth, then you're gonna have short time solutions. I mean, if you start with something that you can make classical sense of all these quantities, then you're gonna have a short time solution. But the question is, what happens with this solution in time? I mean, whether this solution stays regular, develops singularities, or what other phenomena can you observe when you look at this problem? Okay, so as I said, we're looking for classical solutions, but as we're gonna see in a minute, these classical solutions are gonna degenerate, and we're gonna need to make sense of a more broad class of solutions, which is something that people in PDE are very familiar with. I mean, usually in the PDE world, you try to define objects that are non-smooth, there are solutions, and then you try to look for regularity or try to understand in which setting you have regularity, and this problem is gonna appear here, but somehow we also want to give a geometric interpretation to that fact. Okay, so that then I can come to my next topic, that is singularities, and here is where I'm gonna spend most time, I guess, because I want to understand how or maybe not, but this is where I want to understand how the singular behavior happens here. And for that, I guess the easiest thing is to compute some examples, and for that I had actually prepared something for you that I want to share with you in the chat, if I can open it. This is a web page where you can draw curves, that closed curves evolving by curve shortening flow. Curve shortening flow is usually the name that you give to mean curvature flow when you have one dimension. So you can make the experiment yourself of what happens when you draw a curve and make it evolve by curve shortening flow. Okay, so maybe you can do your experiment and tell me what happens by your own, but meanwhile, I'm gonna compute explicitly one example of a curve actually evolving by curve shortening flow, maybe the only example, well, I know, one of the two examples that I know how to compute explicitly. And maybe you can compare what happens with this example that I'm gonna compute and the example that you're looking at. So the example that I'm gonna look at is the example of a circle of radius r. And in this case, well, we only have one curvature, so the mean curvature is just that one curvature. And the curvature here is 1 over r. And if we're deforming the circle by 1 over r in every point, it's natural to expect that the solution is going to be a circle for all times. So the ansatz that I'm going to propose is that I'm going to try to find a solution that is a circle for all times. So it's something that I can write as a radius that depends on time times the unit normal there that I'm going to call omega. And then the normal here, as I said before, the unit normal here is going to be omega. And if you look at my mean curvature flow equation, this is what I call before, I think, sigma. Sigma in this case, I usually call it gamma because it's one dimensional, but sigma of t in this context is going to be r prime
It seems we are having some technical issue with Mariel says. Let me wait. Yeah. Let's wait for her to return. She should be back soon. Yeah, she's back. Jacqueline, can you make her co-host again?
Hello.
Hey,
Sorry,
Maria.
I think I had a technical issue here with the computer, and I'm not sure what happened. It just turned off suddenly.
Yeah, perfectly understandable, Mario, please.
We can see you now.
I'm sorry about that. And then I'm gonna share again my screen. And I was trying to compute the evolution of a circle here. So I was saying that for a circle, we have that the speed is the same for all points. And the normal is just given by this unit vector that this is usually this is the unit vector that goes in the radial direction. So omega of t times the normal, in this case, is gonna be r prime of t. And the mean curvature is gonna be given by 1 over r, but as I said, as I had on my previous equation, you have a minus sign there, and then you get an ODE that is easy to solve, or more or less easy to solve, that tells you that r squared prime is equal to -1, and that gives you that r squared at t is r squared at 0 minus t. And what you can see from this, and maybe if you had the chance of trying in this applet, what happens with the curve, you will see that the curve disappears in finite time. So here, depending on what R0 is, you will see that in a time that depends on what that R0 is, R of t is going to become 0. So R of t becomes 0 in finite time. And that means that the object that was a curve in finite time is just going to become a point and it's going to disappear. And that in terms of the PE of the analytic problem means that you have a singularity in finite time. So the mean curvature flow is something that naturally develops singularities, even in the simplest case. And actually for every curve, as you saw in this applet, if you did the experiment, you will see that this happens for every closed curve. Every closed curve is going to disappear in finite time. Okay, and in fact, this is a theorem. It's a theorem from the beginning of the 80s. That is the combination of two works, the work of Grayson and the work of Gage and Hamilton, that tells you that every simple closed curve on the plane becomes convex in finite time. That's the work of Grayson. And then Gage and Hamilton showed that every convex curve becomes a round point in finite time. And by a round point, if you made this experiment in the applet, you will see that the curve is becoming rounder and rounder when you're closer to the singular time. And that's what they can give a quantitative measure of that you're becoming a circle in some sense as you approach the singularity. In higher dimensions, the situation is even more complicated. You have more directions, so you one expect even more finite time singularities. There are many results, and this is an area that actually this is not completely settled. In some situations, we know how to describe singularities, but in many other situations, we still don't know what are all the possible singularities. So just to give you two examples to have an idea. What happens in the higher dimensional setting. So first, if the initial condition is convex, then it's like the one-dimensional case. Then it converges to a round point in finite time. Infinite time. And this is work of Husken on the mid-80s. But then there's also an example from around that time that what they look is at the following example very concretely, that is usually called the dumbbell example. So it's something that looks like a gym dumbbell, something like that. More regular in the example than my picture, but this also works. And in this example, what happens is that you have a kind of a thin neck there and something that looks more or less like a ball here. So this, in principle, you could think that maybe it's going to do what, if you draw this curve in the applet, you're going to see that a similar curve also converges to a point. But here somehow in this thin part, you have a lot of curvature pushing in here. The curvature here is pushing that direction. And if you balance this in the correct way or in the wrong way, I don't know, depends what is correct and what is wrong, but you're gonna see that in finite time, you're gonna have a situation that is like this, that is gonna have a pinching in the center of the dumbbell. And this is gonna stop being regular, and then solutions in the classical sense are not gonna make sense anymore. You're gonna have a finite time singularities. And then there are many other results that one could mention in this direction. As I said, this is still an active area of research, trying to understand what are all the possible singularities. There are many conditions under which these are classified, but they're not fully classified. It's something that we don't completely understand even nowadays. Okay. So an important tool in all this, not the only tool, of course, but an important tool that you use in the classical setting is the maximum principle. All the results, or many of the results that I mentioned before, are proved using the maximum principle, and this translates into many different ways into the flow. But one basic one is the following: if you have two surfaces. So if you have two surfaces that are evolving by mean curvature flow, and they are disjoint at time 0, so these are disjoint surfaces, then while the evolution is smooth, they remain disjoint. And this is a consequence of the maximum principle. To apply the maximum principle, in principle, you need smoothness, and otherwise you need to have a setup that is correct for applying maximum principle. So for instance, the fact that you have finite time singularities, given that we know how to compute the evolution of a round sphere, the computation that I did for the circle is exactly the same in more dimensions. This doesn't have any change. Tells you that anything that you can enclose within a ball, the maximum time of existence that it can have is the time of existence that that ball that is enclosing has. So we know by the maximum principle that we're going to have always finite time singularities when we're talking about things that are compact. We also know that the strong maximum principle tells you that while things are smooth, they're going to remain disjoint. And in particular, this implies that when you are talking about compact objects, then we're going to have uniqueness for the flow. So another important consequence is in the compact setting, this gives uniqueness. And for now, these are the two applications that I'm gonna mention. Of course, there are many more. These are not the only applications of the maximum principle. This is a very important tool in the field, especially when you're talking about solutions in the classical sense. But as I said before, since you develop singularity, somehow you want to make sense of the evolution, what happens past the singular time, and this is also something that is complicated because somehow you want to give geometric meaning and you want to preserve good properties. So there are many notions of weak solutions that have been used in the past. I'm gonna mention two of them that are the most important, and especially I'm gonna mention one of them that is the one that I'm gonna care about later on this talk. So probably the two more famous ones are the Brachyflow and the level set solutions. The Brachyflow maybe could be compared to the weak solutions in PDE that you do by integrating by parts. But the way that Brachy made sense of this, and this is one actually of the earlier works in Curvature Flow, was from the context of geometric measure theory. And then you allow variables are very general objects or generalizations of manifolds to flow by Curvature Flow. Something that I haven't mentioned, but that is important in everything that I've been saying, is that I'm always assuming that I'm in codimension 1. So I'm assuming that I have n-dimensional surfaces in Rn+1. Many of the things can be generalized to n-dimensional surfaces in manifolds of dimension n+1. But when you have higher codimension, then the situation is quite different. I mean, the evolution is more singular, and many things that I mentioned would not work. In particular, maximum principle doesn't work so well in that setting. Brachyflow allows you to do all that kind of thing, but is maybe the objects are too weak in some sense. I mean, in some sense, there's things that are hard to handle because they're not, I mean, they're very far from being manifolds. So later in the 90s, the Brachyflow is something from the end of the 70s, actually. Later in the 90s, the level set solution approach was introduced by Evans and Sprague, and there's a parallel work of Giga, Goto, and someone else that I'm forgetting right now. And what they try to do is they try to give an interpretation of the viscosity solutions of PDE in this geometric context. So again, level set solution is something that is kind of well understood for things that are codimension 1 and that are extrinsic. So this applies well for mean curvature flow and also for other flows that are of extrinsic nature, not Ricci flow, for instance, if you ever heard of Ricci flow. But they also have some issues. Let me, for that, explain for a second what viscosity solutions, I mean, how you apply the viscosity solutions to this setting. So, okay, so let me tell you what the issues are and why this it reflects on what they are. So the Brachyflow, in general, because it's so general, you have that is highly non-unique. I mean, in general, you have non-uniqueness in this setting. This doesn't happen for the level set solutions, for these viscosity solutions, and I wanted to add a page here. The idea is the following. So the level set solution is the following. So we consider now the surfaces sigma t that I want to evolve to be described in the following manner. They're described as level sets of a function. That's why it's called level set solution. So you assume that this corresponds to having some function u of xt being equal to 0. This is the level set at time t. The problem with this setting, then you satisfy a PDE. The PDE is not hard to compute because basically you do it by extrinsic differentiation here. I mean, implicit differentiation. Satisfy a PDE that is parabolic. And all that is good. The solutions here as I said before, this is linked to what are called viscosity solutions in the world of PDE. So they're in the viscosity sense. If you don't know what that is, it's not important, but what is important is that that only requires you to be continuous. You continuous. And I think I always misspelled that, so I think I misspelled it again. Only requires you to be continuous, but there's this issue. But it can happen that the set, and I'm gonna draw a case where this happens, that the set U equals to 0 is something that is not a surface. It can happen that U equals to 0 is not a surface. So,
Marielle,
what?
I think we don't see what you're drawing.
Oh, really?
Yeah.
Oh.
Or maybe it's just me.
No, maybe it is me. Let me check let me share again. Maybe.
Okay. Thank you.
Thank you. It's not sharing properly. Okay, there we go.
There we go.
Only requires you to be continuous, and there is the picture, but it can happen that you have a fat set that satisfy U being equal to 0. That is what I tried to paint in blue there. So you could have something that is not a surface and still is described in this way. And that's what usually is called fattening, and has the problem exactly that somehow the solution doesn't have the geometric meaning that you want it to have. Okay, so well, with all the technical problems, I may be running a bit short of time. One thing maybe that I want to say additionally is one good thing about the viscosity solutions is that they allow for maximum principles. So this being one important tool in the area, they have that good aspect. They're unique and they allow in many ways to use the maximum principle. Okay, so let me talk about now the topic of today. That was the mean curvature flow of graphs. The mean curvature flow of graphs, I'm assuming that the evolution is going to be given by the graph of a function. I'm going to have to define more carefully what do I mean by this. Then if you assume that you have something that is written in this form and is satisfying the equation, you're going to have something, you're going to have this. This comes from the form of the mean curvature that I showed you a few slides ago for graphs. And there are many things that I'm not saying here that I need to specify. One of them is that if omega is something compact, somehow I need to say what's happening at the boundary. Another thing that you may miss here if you haven't thought about it is that somehow I'm fixing a parametrization by assuming that this is written in this form. By fixing a parametrization, somehow I'm avoiding the problem of this freedom that I have by reparametrization. So all the degeneracies that I'm going to see are exactly because of the form of this equation, and I'm getting away from the freedom of parametrization degeneracy that I could see. So in that sense, this equation is more regular. So yeah, as I said, it's important to think about what this omega is and what are the boundary conditions in this context. So first, I'm gonna look at the easier case, that is when I have all Rn, or maybe not so easy, but in the easier case where I have all Rn, so I don't have a boundary and I don't have to worry about a boundary condition. In that case, that problem was studied in the 90s. Eker and Husken showed that in that case, if you have a function that is just Lipschitz, locally Lipschitz, then you're going to have a solution that exists for all times, that is entire, that is defined in all Rn, so this doesn't develop singularities. And if it's asymptotic to planes, you can even say a bit more about asymptotic behavior. I'm not going to get into that detail right now, but something that I want to point out is that in contrast with the heat equation, you don't need a growth at infinity to show that you have a solution. Somehow, the form of the equation allows you to find solutions for every time, independent of the growth of the function at infinity. But because of the lack of maximum principle, in principle, we don't know if these solutions are unique, or in their paper, they don't really address much the issues of uniqueness, because the main tool to prove uniqueness is maximum principle. And when you have something that is non-compact, like in this case, maximum principle is trickier, it's not so direct to use. Okay, so the next question is, what do you do when you have something that is only defined on a bounded domain? There are many works. I mean, this is not the only one, but this is the one that I want to describe here. That is a work of mine. One option is that you have a bounded domain and you have some sort of boundary condition. This was studied by Husken a long time ago, and the boundary condition can be Dirichlet or Neumann or all the classical things that you do for PDEs. But the problem that we wanted to study was the non-compact case again. And in that case, I mean, you're sort of in the compact setting. It was a non-compact case. What happens if you have a domain and a function that is proper in that domain, in the sense that it's going to infinity at the boundary? Here, the result is written in a rather complicated way, so I want to explain what it means. But I mean, I wanted to put all the hypotheses. That's why I put it in that way. So we're thinking about a domain, and you have an initial condition that at the boundary of the domain is going to infinity. This is going to be my omega 0. And what we show that is that you can find a solution that preserves the properness that goes to infinity at the boundary of the domain, but the domain changes in time. The domain of definition of the function changes in time. So our solution the domain of definition changes in time. You still goes to infinity at the boundary of the domain, but the domain is changing in time, so you have a different domain for every time. And then it's sort of important to understand what is the domain doing. I mean, of course, if you have a changing domain, you want to know how the domain changes. And that's our second theorem that tells you that the domain is actually also moving by mean curvature flow. It's also moving by mean curvature flow. The picture there, so what's trying to depict is the following situation. Is the following situation. Is that you have a initial domain that is an annulus, and you have something that is proper in that annulus. So from what we experimented before from mean curvature flow, the domain is just given by these two curves. And then we know that in finite time, the middle curve is going to shrink to a point. So these two things are going to compare, and then eventually the domain outside is also going to disappear. So an important feature of our solution is that the topology of the solution changes in time and somehow captures, or I don't know if it captures is the correct word, but somehow give us a way of dealing with singularities in the domain. The domain is developing singularities, and the graph that we're seeing above is somehow absorbing those singularities. So it gives you some sort of way of dealing with the singular behavior of the domain. In particular, and now why I was talking about the level set solutions, this can be compared with level set solutions, and the domain coincides exactly with the mean curvature flow, if you have that the domain, the evolution of the domain is not fattening. When you have fattening, when you have that the property that the domain stops being sort of a surface, our solution is choosing some sort of maximality. I mean, it's choosing some part of the fat part, some specific the innermost part actually in this case, and it's giving you a way somehow of choosing a solution. I'm not sure if this is the best way of choosing. I suppose it depends on what your objective is, but it's giving you a way of choosing which part of this fat part you should choose when you evolve by main curvature flow. So that's why it was kind of interesting as well, because it has a connection with the previous results. And given that they have very little time left, I want to address again the issue of uniqueness in all this. In this case, we also, I mean, we pick somehow one solution, but we don't know in general if the solution is unique. I mean, we make a construction and somehow we pick a solution that is maximal in some sense. But in principle, given an initial condition, you could have many solutions, many different solutions coming out of that solution. And because you don't have maximum principle, somehow you again have to deal with that in a different way. And I want to announce a result that is going to be coming out soon. That is work with Toti Daskalopoulos. And what we show is that if you're dealing with graphs that have dimension 1 or radially symmetric, then the solution is always unique. And then if you impose, and in the other cases, if you impose a condition on the second derivatives of this form, this is related to what is called the second fundamental form. It's a geometric quantity. So if this geometric quantity is bounded below, then you're going to have the solution is unique. And then our solution is unique. And somehow, I mean, I wrote it here for entire solutions, but it also applies in the case of domains. In the case of domains, it's going to give you a way of choosing a unique solution. So I think I'm a little bit out of time. I wanted to explain maybe a little bit more about this, but maybe I'm just gonna stop here. I'm sorry for all the technical issues during the talk. Thank you.
Thank you, Marielle. Beautiful talk. So if I understand the settings of the event, all questions, comments are postponed, right? So right. Okay, good. So yeah. So please, if you have questions for Marielle, remarks, comments, please save your comments. And we are gonna have now the talk of Professor Edgar Pimentel, and then we have a discussion maybe with comments and questions to Marielle and to Edgar, more or less at the same time. I have quite a few comments. It was a beautiful talk, Marielle. I think we that work on PDEs, we always like to see those applications in geometric problems. We feel like a little bit useful. I think the analogy is the same thing for us mathematicians, seeing our theories being applied in physics, chemistry, biology. We always feel proud. So somehow I couldn't help but feeling a little bit proud of maximum principle, viscosity solutions, all those techniques being applied in such a beautiful geometric problems. But I'll save my comments and questions for the time of the moderation to make those questions. Okay.
Thank you very much.
Thank you again. So if you can stick around for a little bit, we're gonna have.
I will. Thank you.
Thank you, Maria. Okay, Edgar. So our schedule is kind of flexible. We allowed for 5 minutes to change speakers. That's from the old days that we had to change slides. Nowadays, we have a much more efficient way of doing that, right? So this goes along to what Zezé was saying before. We have to appreciate, of course, this pandemic has been very hard on all of us. but we have to take advantage of the good things that we collaboratively got out of this pandemic, right? And those events like the one that we are holding today, and we're going to have a series of events like this, they somehow are things that we should celebrate, right? Because they imagine to put together this wonderful meeting, how much effort, resources would have been spent, right? Of course, I'm not advocating that we should just banish presidential meetings. They certainly are very important, but it's nice to have these meetings that are more flexible and it penetrates more, right? Okay, so I think I've spoken enough. If you want to share your screen, Edgar,
yes,
I will.
Let me see if it works.
It beautifully. Okay. So I will have the pleasure to introduce Professor Edgar Pimentel. I will have the honor to retribute many times that he introduced myself in the near future. So Edgar received his PhD in 2013 from Instituto Superior Técnico of the University of Lisbon, under our friend Diogo Gomes. After that, he spent a few times in Portugal, sometime in Portugal, and he went back to Brazil. He initially held a position, a postdoc position at INPA, and after that, he held a position in Fortaleza / São Carlos. In 2016, he got Livre Docência, which is kind of an habilitation from USP, which is also an important degree for state universities in São Paulo. If I recall correctly, he held briefly a position at the Universidade Federal de São Carlos before he joined PUC Rio de Janeiro. Currently, he is in Coimbra. And among quite a few distinctions, he is a CNPq researcher. If you are a Brazilian researcher, you know that this is a big deal. If you are not a Brazilian researcher, I'm telling you, this is a big deal. It's a very prestigious sort of a position. He's also a Jovem Cientista of the Rio de Janeiro state. It's also very distinguished. A junior associate of the ICTP. He received a very competitive grant from Instituto Serra Pilheira, and he's also an affiliate member of the Brazilian Academy of Science. So, and today he is gonna deliver a talk on regularity theory from PDE to interfaces and beyond. Edgar, the floor is yours.
Thank you very much, Eduardo, for this very kind introduction. I'm very happy. It's always very nice to meet you and see you. It's an honor for me to be here. It's a joy and a true privilege. I want to start by thanking the scientific committee for thinking of my name. And I do so in the person of my dear friend, Professor Maria José Pacífico. And I also want to thank the organizing committee for putting all the efforts, and what an amount of efforts, right, to get those things done. And I do so in the person of Professor Jaqueline Mesquita. I hope you see my screen, and I hope you see when I change it. Let me see if it's working. It says kind of otherwise. Okay, so today I'm talking about this thing called the generate fully nonlinear transmission problems, and the idea is to start by giving you some sort of general outline of this talk, and what are the ideas and what is the program we'll try to pursue. So the thing is, we start with a discontinuous operator, or with discontinuous operators acting as driving or governing a PDE. And then the important thing and the funny thing here is that those operators are discontinuous, with discontinuities depending on the solutions, right? One consequence of this fact is that, in fact, interfaces arise and their free boundary appears, right?
And then we are not seeing anything.
Oh,
Edgardo.
I'm sorry.
Is there a problem with me or with you, or? Okay.
I don't know. Let me.
No, it's moving. Yes. Thank you, Renato.
Is it? Let me try to do it full screen and see if things work. Well, when I do this thing, I have some sort of message saying that it's paused, sharing is paused. So I don't know. Let me try it again.
There we go. I think it's gonna. There we go.
Okay.
Yes.
Okay. Good. Very good. Thank you. So let me resume. So the thing is, we have some discontinuous operator. This operator is discontinuous with respect to the solutions. As a consequence of this fact, free boundaries or free interfaces arise, and we are interested in two things. We are interested in the regularity of the solutions and also on information about the free boundary or the free interfaces, right? Okay, so this is what we want to do, and we need a candidate, we need some sort of workhorse to pursue this program. And for today, we will stick with this guy. What we have is a fully nonlinear operator, depending on the Haitian of the solutions. And this quantity, this object, is pre-multiplied by the norm of the gradient raised to some power, right? And the power is a theta, depending on x, the space variable, and on the solutions. But this thing has a dependence that is pretty simple. When you are in the positive phase, when you are in the region where the solution is strictly positive, this exponent is simply theta 1. If you change to the region where the solution is strictly negative, then you have another exponent that is theta 2. Without loss of generality, we suppose this exponent theta 2 is strictly greater than theta 1. Well, if you pay attention, there is a third exponent, some sort of theta 3. There is in effect in the region where the solution is identically 0. But this exponent is 0 itself, so we don't get it here, right? And our operator, as for the sake of completeness, I mentioned that this is a lambda elliptic operator, which means nothing but the fact that as you move along positive directions in the space of symmetric matrices, what happens is that the growth of the operator is controlled by quantities depending on small lambda and capital lambda, and the function f is a continuous function that happens to be bounded, right? One other thing that I'd like to share with you, and I'll get back to it further in this talk, is that we also allow f to be merely measurable and essentially bounded, right? But when we do so, we jump from the realm of viscosity solutions to the setting of W2D strong solutions, but then it's also interesting to speculate or to prove results in this context as well. Pretty good. So this is the problem, and let me share with you a picture. There is it's kind of a kid's drawing, but will help me to convey some ideas that I find to be important today. So the thing is, you have the unit pole, and what happens is in the region where the solution is strictly positive, which means this region here, right, where you have the solution to be strictly positive, the PDE governing the process is gradient of u raised to theta 1 times the fully nonlinear operator, right? But then there is another region here where the solution is strictly negative. And in this region, what happens is that the diffusion degenerates as a power theta 2 of the gradient. Of course, here in the region, the remaining region here, in the remaining section of the unit pole, where the solution is identically 0, then we have uniformly elliptic problem. So you see what happens is, if I know the solution and I know where the solution happens to be strictly positive, I know where the exponent theta 1 is binding. If I know where the solution happens to be strictly negative, then I know where the exponent theta 2 kicks in. But the question is, well, for me to know where the solution is positive or negative, I must know the solution. And for me to know the solution, I must know the PDE. But then for me to know the PDE, I must know the solution. And to know the solution, I must know the PDE, and then the loop starts. And this loop is one of the most fascinating things in the context of free boundary problems, right? And that's what adds an additional difficult layer to the whole theory, right? So what happens is we are interested mainly in three things. The first one is the existence of solutions, which by no means trivial in this particular setting. And then we are interested in the optimal regularity of solutions, right? We want to know, well, if you were locally within one of those three regions, the optimal regularity is known. And that's fine. And that's something we know and we are happy about it. But the question is, as you approach the free boundary, the free interface, this wall separating this particular subregions, then we don't know what happens. Now maybe the regularity or the estimates, they might collapse somehow, and we don't know what's going on. So what we're interested actually is in the optimal regularity as we cross the free interface or the free boundary, right? And finally, since now we have a new friend, a new kid on the block, there is this free boundary, the free interface, then we are also interested in produce as much information as possible about this structure as well. But then, well, this is what we dream to do, and then along the way we find some difficulties, right? We face some genuine roadblocks, and we have to somehow bypass those things. The first one, there is not the most difficulty. The most difficult one is the fact that the PDEs hold in unknown regions of the domain, a priori unknown regions, right? So we don't know where the PDEs hold, how to handle the situations. So the question is this question is in fact something that is very familiar to the realm of free boundary problems, right? Something that comes as a gift when you buy a free boundary problem. So this is a difficulty, but it's not the most pressing one. What is really something that jeopardizes our hope here is the fact that the operator lacks properness and some other properties that are very dear to the theory of viscosity solutions. What I mean by properness is some sort of monotonicity with respect to the solution. When it comes to the operator, if the operator is monotone somehow with respect to the solution, then you have properness, and properness is capable of unlocking several properties that are fundamental to the program, right? We don't have this thing. We don't have properness because the way we depend on the solution is through its sign, and then we don't have control on the size of the gradient or how the fully nonlinear operator behaves along the Hessian of the function u as things boil down for us to test whether or not we have some sort of monotonicity. And this is a very consequential fact. Because, for instance, if we lack properness, we also lack maximum principle and comparison principles for the solutions. And in the theory of viscosity solutions, if you don't have maximum principles, you don't have comparison principles, I mean, you better do something else. There is no way those are fundamental building blocks of the theory, and if they are not available, then there's not much you can do, right? So the thing is, we don't have properness, we lack several foundational results. So what do? The idea here is to say, well, we have to look at further structures. We have to examine some other things and try to pair the problem with some other structures, and then see if we have some strategy to import information from these other structures back to the original problem, right? This is what we will try to do, and this is how we'll try to bypass this difficulty. Right. So before I talk to you about the things we did, let me share with you some information on previous results, previous problems, and things that are very inspiring, and they were very inspiring to us when studying those problems. So the first thing that occurs to me, and that occurs to most of the people in the field, when we talk about discontinuous operators, discontinuous PDEs with dependence on the solutions, is the obstacle problem or the classical obstacle problem. What happens here is that you have a Poisson equation, so Laplace of u equals to something, And this something is the characteristic function of the set where the solution is strictly positive. And here you consider non-negative solutions. So you see, you have a very simple operator. Well, you have the Laplace operator. Not that it's simple, but it's somehow the way you enter the theory of second order PDEs, right? And on the other hand, you have the right hand side. There's the characteristic function of the set. Of course, this is a discontinuity. It entails its continuity. There is solution dependent, and then a number of questions can be posed. This problem has been studied, I mean, largely examined in the course of the last 50 years by very smart, very intelligent people, doing a number of producing a number of developments for the theory, and it covers regularity of the solutions, geometric properties of the free boundaries, and a number of important variants of the model that you just see here. If you're interested in this topic, there is a monography, neatly written monography by Arshak Petrosian, Shagolian, and Nina Rautseva that appeared in 2012 in the AMS book series, Graduate Texts in Mathematics. And this neatly written is a very nice way of getting acquainted with this topic, and somehow has a number of motivational paragraphs in this book that I find to be really valuable. But one thing that I find to be very important about the obstacle problem is not only the results that have been proved about it, but much more the way it informs which questions to be asked when you face a similar situations. And those questions should be about the optimal regularity of the solutions. In fact, it's known that solutions are of class C11, and in addition to that, the optimal regularity of the solutions, and also regularity or geometric properties of the free boundary. And there is one thing that I happen to find very interesting. There is about the structure theorems for the singular sets, right? Here you have a dichotomy about the free boundary, and the free boundary can be decomposed as a set of regular points and a set of singular points. And then the regular part of the free boundary behaves very nicely. But when it comes to the singular set, it's important to understand how the geometric properties of this thing. And it comes to the fact that the interesting thing here is to find the regularity of the supermanifolds that locally cover these points and give a lot of information about this structure. So you see a very nice problem, attracting very nice people, and also informing very nice questions when you try to proceed in the field, right? There's a second class of problems that I happen to find very, very attractive, very interesting. There are so-called unconstrained free boundary problems, right? Here what you have is this. You have a very simple equation, FD2U equals 1 in a subregion of the unit ball. And what is special about this subregion is that in this subregion, let's call it omega, the Hessian of the solution is strictly larger than K in norm, right? And K is whatever you want. It can be 1, can be 1983, can be whatever you decide. The thing is, you control the Hessian and B1 minus omega. And in the region where you don't control it, you have the PDE. Is there anything you can say about solutions? And not only that, is there anything you can say about associated free boundaries for this problem? I say this in the plural because you see, one of the important things about this problem is that it accommodates a large class of obstacle problems, depending on the gradient as well, depending on the solution itself, depending on several properties. So this is a very interesting problem. It was introduced in 2014 by Alessio Figalian and Shagolian, a very consequential paper. And a couple of years later, Emanuele Indrei and Andreas Mine worked out a few details on this problem, slightly pushing forward the theory, right? What is very interesting here is that you see solutions can be proven to be locally of class C11, right? So in the context of these unconstrained free boundary problems, you are capable of recovering the optimal regularity available for the obstacle problem, right? And then, well, once you have the optimal regularity of the solutions, then you start paying attention to the free boundary. And what happens here is that, well, under a very natural assumption, and this context has to do with the zero, the complement of the zero level set for the gradient, then you can retrieve information on global solutions, in fact, by proving that they are half-space solutions, whatever it means. And you can also prove that the free boundary is, in fact, locally of class C1, right? So you see, you have a different problem, a different type of problem, but still it's meaningful, and it is very meaningful and consequential, and still you can recover the same type of results. Optimal regularity coinciding with the one in the obstacle problem. You can show important facts about the free boundary, and you can establish this program as something that advances the theory. Right? Well, but you see here the discontinuity in the obstacle problem, in the unconstrained free boundary problems, the discontinuities appear on the right-hand side, right? You have the operator, but then the discontinuities appear on the right-hand side, depending on the solution, but still the operator is given, right? You have either the Laplacian or the fully nonlinear thing, and this is not discontinuous across the domain, right? If you are interested in things that are discontinuous at the level of the operator, then, well, the class of problems that has to do with it is the class of transmission problems. And what is a transmission problem? You see, at first, you consider a given domain, let's say it's B1, and then you fix a compactly contained subset, let's call it omega 1, right, in the unit ball. And once you have this guy, you can define omega 2 by saying, well, omega 2 is the unit ball minus the closure of omega 1, right? And then what you say, well, you have two subregions of the domain of your unit ball. What you say is, well, in one of those regions, you have divergence of A du, and in the remaining region, you have divergence of B du for constants A and B. Here, this can be constants, could be scalars, could be matrices, could be your favorite. When you think of constants, whatever you think, right? And of course, it would be polite to equip the boundary of omega 1 with some sort of boundary condition. This would be, in fact, a transmission condition across this interface, right? And then you see this very simple example. What happens here is A and B are matrices. So you can think of this function U as being harmonic. And what happens is that inside, locally in the interior of omega 1, you have a harmonic function, the same thing in the interior of omega 2. But what happens as they cross the boundary of omega 1, given the boundary condition, is what we're interested in, right? How this transition, how this discontinuity in the process affects regularity. One of the key words here is the fact that the interface is known. The interface is known, is prescribed a priori, right? This class of problems was introduced in 1954 by Piccone, and a number of results on the existence, on uniqueness of solutions, and then also on variants of these problems in the realm of applied mathematics concerning elasticity, mechanics of solids, and this kind of stuff appeared, right? It would be only in the year 2000 that people would start studying transmission problems from the perspective of regularity theory, trying to produce estimates and this kind of information. It was somehow launched by Bonnetier and Vogelius, Lee and Vogelius, Lee Nirenberg, Paul Yin, Brian Capdeboschi and Nguyen, more recently, Luis Caffarelli, Maria Soriacavo, and Pablo Raul Stinger. You see, what happens here after year 2000 is that, well, you try to prove regularity information for the solution based on what you have as a regularity for the geometry of the transmission interface, right? And several interesting things here appeared. I mean, if you have multiple inclusions, multiple subregions, then somehow you want to understand how the estimates blow up as these subregions approach each other and this kind of stuff, which is very, very interesting. I mean, this recent work by Luis Caffarelli, Maria Soriacavo, and Pablo Raul Stinger, in fact, what the authors do is, well, they consider harmonic functions in two subregions of the unit ball, let's say, and then you prescribe the minimum regularity for the interface and is capable of importing this regularity to the solutions. I mean, this is a This is a very nice idea. I mean, I never mentioned anything that happened between the trailblazing work of Piccone and the beginning of this study of this problem in the context of regularity theory. For that, I strongly suggest this monography by Borzuk that appeared in 2010. And this is a very nice book. This is a very nice book covering, somehow bridging the gap between the launching of this class of problems and the beginning of the study of these models in the context of regularity theory, right? But this is a known interface, right? This is fixed. What's the question? The question is to say, well, what if the interface depends of the solution? And this question, well, this question launches the class of free transmission problems. This question was posed by the first time, 2015, by Marcelo Amaral and Eduardo Teixeira. And more recently, there's a work by Maria Colombo, Sung-Han Kim, and Henrique Chagolian. They also address this question. What happens in these works is that, well, you have a transmission problem, you have this discontinuity, you change regimes, the diffusion process changes abruptly across an interface, but what happens is that this interface is unknown a priori, right? It depends on the solutions, and typically what you do is you go from the positive to the negative phase, or from the positive to the identically zero phase. But then you depending on the sign of the solution, you have a different set of coefficients driving the problem, right? So let me talk to you a little bit about this recent work of Maria Colombo, Sung-Han Kim, and Henrique Chagolian. Just somehow I would say mimics, but it's not that it mimics. Somehow it relates to what we do in the context of a variational problem, right? So you have this PQ Dirichlet energy, where P is binding when it comes to the negative part of the solution, and Q is binding when you have the negative part of the solution, right? And then the question is, well, P and Q might range between 1 and infinity exclusive, they are different, and you have an open, not necessarily bounded subset of RD. Then what happens? What happens is that, well, there are minimizers, there exist minimizers, and minimizers are Hilbert continuous functions, right? What is funny here, there is an estimate for the Hilbert norm of the minimizers, and the authors produce an explicitly blow-up rate for this estimate. And it's very neat in the sense that it's like those embedding conditions you have, 1 minus the dimension over P or Q, depending on from which side you come, right? And the other thing is the C1 alpha regularity of the free boundary. This is an interesting result. And one interesting thing is, well, there's a P harmonic measure. There's this P Laplace acting on the positive or negative, but here the positive part. And this is a non-negative Hadron measure who supports the subset of the free boundary, right? And there are other results concerning the regularity and measure theoretical considerations about this thing. One thing that I find very nice, because you can indeed formulate to a grad student or at the high school level, and it's very easy, very simple to formulate, though it's very hard to prove, is the fact that the support of this non-negative Hadron measure is in fact sigma finite with respect to the d-1 Hausdorff measure. I find this to be a very nice thing. Well, so this is what happens. This is what happened in this context of free transmission problems, variational free transmission problems, right? And you have some sort of, I don't want to say tangentiality, but you are somehow close to this P Laplace structure where you have a gradient raised to some power, degenerating a diffusion process, and this kind of thing. So what I want to continue by telling you is what happens in the context of our model. So what you have would be a degeneracy degree depending on the solutions in the model that I just showed you at the beginning. So you have the gradient raised to this weird exponent times the fully nonlinear operator, and there is a source term small f. It happens in B1, and the exponents are somehow ordered, they are fixed, they are constants, and theta 2 is supposed to be above theta 1, right? So the more important question at this point is, well, why would someone study a model like this, right? Why would someone be interested in multiplying a fully nonlinear operator by the norm of the gradient raised to this, right? You see, the answer starts with this, with the simpler, with this PD here, right? What you have is a fully nonlinear operator pre-multiplied by the norm of the gradient raised to some power theta, and you have the source function f, right? And what happens here is that, well, let's say it's not really necessary in some of the cases, but let's suppose we have a degenerate case instead of a singular one, which means that theta is strictly positive, and f is a continuous function that happens to be bounded, right? So it's been studied by a lot of people since the beginning of the year 2000, and a lot of authors actually proved important things about the solutions to this model. It ranges from Liouville type of results, comparison principles, results on spectral properties, and all those things, ABP estimates, and of course regularity results. So an interesting result that's been proven by for this model concerns the C1 alpha regularity of the solutions. It was first proved by C. Hillenberg and Luis Silvestri in 2013. And what happens there is, well, solutions are C1 alpha for some alpha, right? A few years later, Damião Araújo, Gleidson Ricarte, and Eduardo Teixeira proved, well, it's true, it's C1 alpha for some alpha, but alpha is either the exponent coming from the C1 alpha regularity for the homogeneous equation driven by f, or is precisely 1 over 1 plus theta, right? So in fact, the result by Araújo, Ricarte, and Teixeira, what it gives you is an explicit account of this interplay between ellipticity and degeneracy, right? And you have in front of you how those things actually behave, right? There's another take on the regularity of this problem that I happen to find very interesting. There is the idea of equations that hold only where the gradient, elliptic equations holding only in the regions where the gradients are large, right? And this was first studied by C. Hillenberg and Luis Silvestri, and in the context of merely measurable data by Conor Mooney in 2015. Right? The consequence of the results here are some sort of Krylov-Stefanov theory, in the sense the authors produce C0 alpha estimates. Right? And another thing there is related to this problem has to do with the case of variable exponents. I mean, the theta can depend on x, right? And it was studied in the case, involving the case of singular problems for f in continuous and essentially and bounded source terms. And the optimal regularity has been proven to be C1 alpha, where alpha depends on theta. And although theta is assumed to be continuous, it's assumed to be continuous by formality, right? In the sense that the results don't depend on its models of continuity. And it was a very nice adventure to study this problem in the nice company of Annie Bronzi, Jerry Rampasso, and Eduardo Teixeira a couple of years ago. Well, so now that we know those things, let me tell you why would someone multiply a fully nonlinear operator by the gradient raised to some power. So at one instance, it accounts for a non-variational counterpart of the P Laplace operator. And to some extent, this is good enough of a motivation for me, but it's not a mathematical statement, right? So when it comes to a mathematical statement, you can phrase the motivation as the idea of studying fully nonlinear operators satisfying further structure conditions. In fact, if you go to the definition of ellipticity in terms of extremal operators, instead of saying, well, dependence is controlled, the difference is controlled from above by the Puch operator plus something, the dependence on the gradient would be multiplicative for symmetric matrices and a vector in RD. So I find this to be nice motivations to study this class of problems, and I think one interesting thing would be to somehow further the understanding of the class of LP viscosity solutions under those structural conditions, which I find to be very interesting and very, very difficult. Okay, so let me share with you the results we have about it. And the results I'm sharing with you today were obtained in collaboration with Gerardo Aroto from Universidade Federal de Alagoas, Gianni Rampasso from Universidade de Campinas, and Andres Fior from GATEC in Atlanta. And then what happens is you'll take your favorite number, alpha. There's between 0 and alpha 0, and below 1/1 plus the maximum of these exponents. And here, alpha 0 is the exponent governing the C1 alpha regularity for F equals 0, right? And then you suppose one of two things. Either F is a continuous bounded function and use a viscosity solution to the equation, or F is merely measurable and essentially bounded and use a W2D, the strong solution. So in either case, what you prove is that solutions are in fact C1 alpha with appropriate estimates, right? And of course, the alpha is the number you've chosen with this satisfying both these constraints here, right? What do I mean by appropriate estimates? Appropriate estimates here are estimates according to Nirenberg, which means that we control the C1 alpha norm locally by a constant L infinity norm of the solution and something depending on the right-hand side. Here in this case, the dependence involves very much the exponents, right? Well, we have also a Hilbert continuity of the gradient under F merely essentially bounded. So this is a new result in the context outside of the viscosity, C viscosity realm, right? The regularity known outside of the C viscosity realm was C0 alpha, and somehow to this particular model, we managed to give some information above this threshold. I like very much this thing, C viscosity, LP viscosity, and how this thing play a role in the regularity theory. We actually finished, and this is kind of a propaganda, we actually finished a set of notes on elliptical regularity theory by approximation methods that actually starts with this discussion, trying to compare those things and this kind of stuff. Well, so how do we prove this thing? You see, the operator, as I told you before, lacks properness, and when things lack properness, we are very much in trouble. So what we do is we observe that if you solve, in whatever sense you're considering, our equation, then it also solves two viscosity inequalities. The minimum between these three things is bounded from above by the L infinity norm of F, and the maximum of those quantities is bounded from below by minus the norm of F, right? And once we do this, well, we get a ticket straight to the user's guide to viscosity solutions by Michael Crandall, Toshishi, and Pierre Billions, and we can apply all this machinery and all this technology to the problem, right? It allows us to use or to conclude compactness and use approximation methods. Here we combine the maximum principle. There is also known as the Ishii-Lyons lemma, or Crandall-Ishii-Lyons lemma, or Ishii lemma, and the result due to Imbert and Silvestri. And the funny thing is that solutions, which allows us to conclude the argument, is the fact that solutions to this viscosity inequalities, in fact, solve the homogeneous equation driven by F, right? So when combining these two main ingredients, the proof of the optimal regularity actually follows. So you see this fact here that solutions to inequalities actually solve an equation, actually solve a PDE. This is rare, right? This is not usual the case. I mean, of course, these inequalities depend and are built on this operator F, but in general, this is not something you would expect. You see, if you suppose that U satisfy, I don't know, suppose U satisfies these inequalities driven by the extremal Puch operators, right? A natural question one could ask is the following: is there a lambda-lambda elliptic operator G such that G of D2U is 0, right? Because you see, the extremal operators are related through 0 by inequalities, we are after an operator that would somehow fix zero and have U as a solution, right? Well, you see, were the answer to this question affirmative, then you would satisfy these inequalities here, where E is a direction in the D-dimensional and in S12, right? S12 or so, the sphere in RD, right? And why am I fixing the sphere in R12? Well, I'm fixing the sphere in R12 because, in fact, I want to resort to this counterexample by Nadrashvili-Vladut in dimension 12, right? So if the function is precisely the counterexample, then we would have something like this for some vector in the sphere and some small value of h, right? Well, but if this is the case, I apply once again the property and I conclude that the gradient is of class C1 alpha, which is clearly false because I was considering one of the counterexamples to C2 alpha regularity. So the question is, usually and in general, if you have 2 inequalities, 3 inequalities, 17 inequalities, it doesn't ensure you, 17, I don't know, but it doesn't assure you that the solution to those inequalities is indeed a solution to a PDE. There is an operator, right? There is an equation, right? And in the context here, this is true, right? And although I like the result, I think I like better the techniques. I mean, these techniques of using these viscosity inequalities have been adapted and advanced by two authors. First, Cristiano de Felippes, who studied non-homogeneous degeneracy, and David Jesus, who also studied this class of problems in the presence of variable exponents. And one thing that David noticed is that if you go through these inequalities, these viscosity inequalities, then you can allow the exponent to depend also on the gradient. David is a doctoral student here in Coimbra, working under the joint supervision of José Miguel Urbano, Professor José Miguel Urbano, and myself, and did a very nice job on this topic. We also used this kind of technique through those inequalities in the context of uniformly elliptic setting, and it was done jointly with Maxon Santos. And this was the strategy to, in a similar problem, though uniformly elliptic, recover maximum principle and pre-compactness, right? And one thing that we could do, and I don't know why someone would be interested in that, but one thing we could do is to consider discontinuous variable exponents whose image of the unit ball would be a countable set, right? So you have some sort of Bellman equation where the control is the exponent. I don't know if someone would be interested in this kind of model, but anyway, it's something that the techniques would allow us to conclude. So let me talk a little bit about the existence of solutions. I believe I have some 5 minutes. I'll try to spend talking about this thing. You see, the existence of solutions in the context of viscosity solutions is kind of a straightforward matter if you have a comparison principle. Right? If you have comparison principle, then you have to cook up some barriers, and then you end up with subsolutions, super solutions. The comparison principle in Perron's method assures you something in the middle, and this something in the middle solves the problem, and you're in business. The question is, as I mentioned before, we lack properness, which somehow jeopardizes any sort of comparison principle at the level of the equation. So the existence of solutions became something interesting for us to pursue due to this difficulty, right? And then what happens is this: well, you need some geometrical condition on the domain. We chose to impose a uniform exterior sphere condition. Could be a cone condition, but then the constructions wouldn't be explicit. But if you impose a uniform exterior sphere condition and you have a function f that is continuous up to the boundary of the domain, and a function g that is continuous on the boundary, then it's true that this Dirichlet problem has a viscosity solution, right? One thing that I want to draw your attention to is the fact that here it's a zero, right? It's u strictly greater than 0 and u strictly smaller than 0. Because you see this typesetting here, it seems to be a no. And I think in the archive version of the paper, I have a typo, and instead of a 0, it's a no, right? A good friend of mine noticed. But you see, you have a usual geometric condition on the domain, and you have continuous functions for the data. Then you're capable of proving the existence of solutions to this problem. Well, the main difficulty here is, of course, the lack of the absence of a comparison principle. So we have to bypass this thing. How do you bypass this thing? So you take a continuous function v and some epsilon between 0 and 1, and you consider a new friend of yours. There will be this sort of regularization. You see, here you add an epsilon to the gradient so you don't degenerate. Here you add epsilon nu because you want to prove a comparison principle. You want somehow to account for the value of u to get a contradiction in the end. But here you have a regularization of the exponent. And the regularization depends on v, not on nu. So you remove from the exponent the dependence on the solution, and then at this level, you manage to prove a comparison principle. A comparison principle is available. Well, if a comparison principle is available, we can prove the existence of appropriate various super solutions, and we prove the existence of solutions to this regularized problem. Well, then what do? You let epsilon to 0, and you end up with the existence of solutions to this equation here. There is more or less what we had before. You see the way I sent epsilon to 0, the parentheses here, the brackets remained. It was just I was copying, pasting, and erasing the epsilon plus, and then we have this guy. You see, sometimes you get to the limit in a very fancy way. But you see, here, what we have is we have du raised to theta v, right? And then we start an iterative scheme. V is u1, u is u2, and then you start solving for un plus 1, plugging un in the exponent. Once you do that and you send n to infinity, you conclude the proof, right? So you see what happens is the talk is very much about this thing. We have a model. We don't know what to do with this model. It breaks down very early in the theory at the beginning, and we don't know what to do. So you just have two ideas and they unlock the program, right? Well, they unlock partially the program, right? Because there is a lot of things we want to know and we don't know. And I mean, we are very sad about it, but we hope we can learn about. So the first thing is how many free boundaries are here in the problem? Of course, you have the transmission interface where u is positive, u is negative. You have the boundary of the sets. This is one thing. But you also have the free boundary problem driven by the gradient. Where the gradient vanishes, the equation collapses, right? So you have more than one free boundary, and somehow it unlocks a theory of free boundaries in the higher codimension. Because you see, if you have C1 alpha functions, the set where the gradient vanishes very much relates to the set where the solution, where the solution vanishes as well, right? And we would love to prove a dichotomy for this problem, splitting the free boundary between regular and singular points, also studying structure theorems and pursue a responsible and well-done analysis of the free boundary. All those things are things I'd love to do, but I don't know even how to start, right? But the good thing is that I recently moved to the lovely city of Coimbra, where I took this picture. And you see, as soon as those clouds, those dark clouds dissipate, I hope people get back in the air and can come here to visit us. And jointly we'll be able to tackle those questions and celebrate mathematics. With that, I thank you all very much.
Awesome. Thank you so much, Edgar. Very nice talk, beautiful talk, as a matter of fact. So following the protocol, I would like to invite Mariel to the floor again, and then we should have maybe 5 to 10 minutes discussions in terms of questions, remarks, all these things. So I open the floor for questions, if you have any. I would like to start, while I wait for people to talk, maybe I would like to make a comment on Mariel's talk. So as I was saying before, it's always very nice for us that work with these hardcore PDEs and these techniques. And I was very happy to see the connection. And I hope everybody could see the connection between these two talks, right? The viscosity solutions that Edgar was mentioning, the problem that he had was precisely the lack of maximum principle, and Mario very, very nicely pointed out that these are the main techniques to prove those beautiful geometric results. So Mario, I was thinking, would you say that, for instance, if you take the classical result that you mentioned in the middle 80s, I think, for the existence, are they PDE solutions or they are geometric results? I mean, they are geometric results, of course, but do they prove by pure geometric, pure PDE?
No,
use?
it is PDE. It's absolutely a PDE tool, and what I was mentioning at the beginning, that you sort of need to choose a parametrization is part of it, but after you choose the correct parametrization, then you have a PDE in the classical sense, and you can apply the standard theory. So it's really a PDE result, and then you want to make the bridge with the geometric part. I mean, basically show that any other solution is the same solution from the geometric point of view.
So if I understood correctly, depending on the parameterization that you use, you end up with a different PDE, but it's really a different PDE. It's not in the same class. It's not that you're changing PDE.
It is at the end the same PDE, but somehow you need to show that it's the same PDE. You get an extra term that comes from it's a tangential term, basically, that comes from the parametrization. And usually there's a standard way of choosing the parametrization, so you have a uniformly elliptic PDE for short time. That's basically what you're doing. Parabolic.
I see. And if you're not smart enough from the beginning to choose the correct parameterization, you're going to end up with something that may degenerate.
Yeah, exactly.
Okay. And it's not only the coefficients, it's more than that.
It's mostly the coefficients. It's the ellipticity constant that may degenerate if you choose wrongly. But this is something that you see even when you parameterize curves, right? That if you choose the wrong parameterization, you don't get a tangent vector.
Exactly. Yeah, exactly. Yeah. Excellent. Very good. Thank you. So if you have any question, you can speak up or you can leave a comment on the chat. Before that, Edgar, it was a very nice talk, very beautiful talk. It's a very nice, it's close to my heart, of course, but those are very interesting subjects, very difficult problems. And I found particularly interesting that the existence proof that you were mentioning, because it, from what I understand, it seems to me that you don't have those techniques of available to you at maximum principle and so on and so forth. But one way to interpret those regularity results that do not depend on the continuity is that, okay, you don't have these techniques, but you have compactness. So, I mean, you may not be able to prove existence because you don't have the techniques, but if you allow some poetic literacy, the solutions may not exist, but you have compactness, right, on approximating scheme.
Yeah.
And it was a very nice idea to change U to V and sort of find a fixed point, right? Because you're doing these recursive idea, which are gonna end up to a fixed point, and you can do that because you have compactness. So up to subsequence, you can pass the limit, and things should work well, right?
Yes.
I was listening to you, and I was curious to see, can you set up? If you set up, you could set up the problem as an operator, right? You set up an operator, let's say capital phi, define on the space of continuous functions inside of the space of continuous functions, that for each v assigns phi of v, which is u, which is the solution of the PD when you plug v instead of u, right? So you have an operator from the space of continuous functions inside of itself. right?
Yeah.
Have you guys taken a look at this operator? Because it would be very interesting to prove like nonlinear functional analysis properties of this operator, right?
Yes.
Because it is a compact operator in the sense that it maps bounded functions in compact
operators. This is a very nice question. Yeah, this is a very nice question. I mean, because you see, one thing you have to do is you have to introduce this epsilon, because you need some room for you need some room for theta to move from one regime to the other, right? So you would have an operator for every epsilon level. At every epsilon level, we would have an operator. So you would have a family of operators. They would be compact, and with some sort of supernatural help, we would be able to prove that the dependence on epsilon is good, right? You have the operator and you saw it's good. And then what happens is that by the end of the day, probably you could have this operator ranging in these two regimes. You have the epsilon, you have the space of continuous functions, and then you can somehow extrapolate to other classes of problems. I see this type of technique, as you mentioned, we haven't thought of it, but as you mentioned, I can think of it, as you mentioned, as something that would help us very much to understand regularity issues in free boundary problems in the absence of monotonicity formulas.
Yeah,
but as a wild guess.
Yeah. Thank you so much, Edgar. Thank you, Mariel. Do you have any comment or question? So if not, on behalf of everybody involved and all the audience, I thank you, Mariel, again.
I have a little comment and question.
Oh yes, Renato, please.
About the applet. It is a wonderful applet. I like it very much. How difficult is to construct something similar in 2D for the surfaces and not for only the curves?
That's a very good question. I don't know. I think it's not very easy. I mean, there are people that worked on numerical geometric flows, and I think there are some things, but I haven't found like anything like this. It would be nice. I would love to have something like that. I don't know. Yeah.
So you did it? You did?
No. I know. I know that there are some things. I've seen some simulations done by other people, but I don't know how they do it. So I know it exists, but I don't know how they do it.
Oh, okay. Yeah, nice.
Yeah. In any case, I think this one is based on something that is called Curve Evolver, that is in the page of Ken Brackett, actually, and you can download it, I think. Just this is nice to share on talks.
And I also, one thing, I have to say that when in the first 5 minutes of your talk, the title was the mean curvature, the mean curvature flow in graphs. Yeah. So I immediately thought, not in graphs as the graph of a function, but in graph like points and lines.
Yeah.
Do you know anything kind of that discretization in that lines of I mean, I guess probably you could put a discretization of the flow and think something like that.
No, I mean, this is a very interesting question, and actually this is a difficult question. It's something that I actually have worked on. What usually you think about is a graph that each curve evolves by by curve shortening flow, and the nodes move somehow. I mean, they're linked by the fact that the curves need to stay connected, and because they're minimizers, you also put an angle condition on how this evolves. And this gives you an evolution, and this is a difficult problem because it's degenerate. This is more degenerate than regular curvature flow. And also there are numerical simulations of this. I mean, this is something that actually has very concrete applications, I think, in material science. Sort of the original problem comes from there, I think.
Can you repeat what's the idea of the discretization? I mean, you have the graph, you have points and lines, and
you have, let's say, a domain and some outer points where this graph join on some initial condition that is a graph in the sense that you have a set of nodes and a set of curves joining these nodes.
Curves, not straight lines.
No, curves. And then what you do is you allow each curve to move by mean curvature flow, each of these curves, and then you add an additional condition at the node. At the node where the curves meet, they have to meet in groups of 3 in 120 degrees, because this is a minimizing condition. And this tries to find a minimizing network that joins the boundary points. That's what it's trying to do. But, you know, like, it's not known in general if it works. It's known in some cases.
Okay. Thank you.
Yeah, thank you. This is a very, very interesting problem, actually, and a difficult one.
Very nice, Renato. Thank you. Okay, guys. So I thank you all for your participation. A special thank you for Mariel and Edgar. Beautiful talks, very inspiring talks. And we have a small break. I'll stick around here, but we resume at 11:40. Let me double check that. Just that I don't say anything wrong. We resume at 1:10 p.m. Brazilian time. So you do the change, right? For me, it's 12:10. So at 1:10 p.m. Brazilian time, we resume with Gustavo Ponce, the moderator, and our first speaker will be Professor Felipe Linares. So I look forward to it. I'll stick around here, and I look forward to seeing you all guys together in a while.
Good afternoon to the people in this part of the world, and good morning in this side. It's a real pleasure to be the moderator of this afternoon section. I would like to thank the organizer for giving me this opportunity to introduce these two speakers. And the first one will be Felipe Linares, who is at IMPA since 1992. And he will be talking about the Cauchy problem for the L2 critical generalized Sakharov-Kuznetsov equation in 3 dimensions.
Okay, thank you, Gustavo, for the introduction. And I would like to thank the organizer for this nice invitation. This is it's an honor to be part of this conference. And then today I would like to talk about this equation. It's called Sakharov-Kuznetsov equation. And basically, I'm taking this example, and I will tell you about several things that we work in nonlinear dispersive equation, and this is a nice example to follow. Okay, so the equation that we have in play today is this one here. So we are in dimension 3 in this spatial variable, and this is a temporal variable t. And here we have the Laplacian in all the variables x, y, and z. And you have a nonlinearity here. This is a particular nonlinearity. And then I will try to convince you that this is an interesting problem. And it also has a nice property that we should work. Okay. So the outline of the talk is as following. So I'm going to give a long motivation, talking about what has been done for this Sakharov equation and all the family regarding the Sakharov-Kuznetsov equation, or CK equation. Then I'm going to tell you about some result that we get for the local well-postness, global well-postness for this initial value problem. So I'm going to make some remarks, and I'm going to give the idea of the proof, basically what are the ingredients of the main result, and the local result. And then I'm gonna list some open problems that actually will summarize what we have done and what we need to do next, right? This is a joint work with João Pedro Ramos, and now he's in the ETH in Zurich. Okay, so the question that I want to address today is a generalization of this one over here, k equal to 1, right? This is called the Sakharov-Kuznetsov equation, and I had the chance to give a talk in Theorem in 2017. It was the American-French conference there. And then these two guys, Vladimir Sakharov and Evgeny Kuznetsov, were in my lecture. Okay, so these are two figure guys there. And this picture were taken by Svetlana Rudenko, and thanks her for this picture. Okay, so that's a nice thing to say. Okay, so the equation, actually the equation that came out from the physical situation is this one here. So Sakharov and Kuznetsov model long wave small amplitude limits of the Euler-Poisson system in cold plasma, and they came out with that equation. All right. So this is physical in dimension 2 and dimension 3. So a long time ago, it was in 2012, together with David Lance and Jean Clouseau, we give a rigorous justification of the equation. All right. So we have a physical model, and that will make sense of what we are going to do in the next few minutes, right? Okay, so one property that this equation has is, or doesn't have, is not completely integral, right? So then nowadays, completely integrable systems are in fashion again, but this Sakharov-Kuznetsov equation is not. All right. Let me see if I jumped something. And then you have these quantities. This is invariant by time, so you have the mass invariant by time, and the energy is also invariant by time. Okay, so these two quantities here are very useful if we need to extend local solutions to globe. All right. Then there is a comparison mathematically. You can compare this equation, the CK equation, with the Korteweg-Debris. Okay, even though the physical situation is completely different. Okay, so CK is propagation in plasma physics, and Korteweg-Debris equation was first derived to describe propagation of nonlinear wave in shallow water. Okay, so in 2D and 3D also, the equation that share the same properties of KdV is called the Kandostek-Pesviev-Billy equation, KP equation, that we are going to hear after my talk. We're going to hear Claudio talking about that equation. And you see, this is a non-local problem, right? And there is a non-local operator different from what we have here. Even though the local theory here, depending on the sign, is much better than the one for the CK equation, okay? Even though the CK equation is local. Okay, so since I'm going to talk about well-postness, I should say what I mean by well-postness in this talk. Okay, so we have a nonlinear dispersive equation, right? And then we are going to follow Cato definition. So that means we include existence, uniqueness, right? Continuous dependence, but also we include persistence. And that means that if you started with initial data in a functional space X, then the corresponding solution describes a continuous curve in X, okay? And then, as usually, if t, the time, so you can solve for a small time. So we say that this is locally well posed. Otherwise, we can say that this is globally well posed. In most of the dispersive model, nonlinear dispersive model, the natural space to work with are the Sobolev spaces, HS, and I leave the definition here. It's just the temporal distribution such that this weighted function is in L2. Okay, so every time I'm going to talk about this space and functions in that space. All right, so the first question is, okay, you have a problem, and then you would like to know where to solve this problem, right? So if you have a equation with homogeneous symbols, right? So it's easy to try the following argument. So this is a scaling argument. So you got a solution of the problem with initial data you note. And then you notice that here, for this equation, we got that this function here, with lambda positive, with initial data like this, is also a solution. And then what we do is to measure the number of derivatives that leave this quantity invariant. Okay, so if you do the computation, you get with this parameter here, lambda, and then you have this coefficient. All right. So what we expect is to have local well posedness if S is greater or equal than this number here. And that is because if you are below this number, so there is a problem with the continuous dependence. All right. So this is the point that we should start, okay? So we expect to have local solutions in these Sobolev spaces whenever S is greater than this number, okay? So, but that's just a guess. Sometimes you can reach that number, some other times you cannot reach, okay? But this is a starting point. All right, so I got now I'm gonna tell you what is the state of art in regarding the local well posedness, global well posedness for these models related to CK equation. Okay, so the starting point here is with k equal to 1. 2 dimensions, and that started in 1995 by the work of Faminsky, where he proved local well posedness in the HS S greater or equal than 1, but S integer, right? And his method of proof was combined smoothing effects, right? And a contraction mapping principle. Then in 2009, together with Ademir Pastor, we extended the result of Faminsky for NES real and greater than 3/4. And we were motivated by the work of Katie Ponce and Vega for the KDB equation. Okay, so we got local well posedness at the time for S greater than 3/4. Then there was a major improvement in 2015. So independently, Molinet and Pilot and Grunrock and Hare show, using Fourier restriction method introduced by Bourgain, that the problem is local well posed in HS for S greater than 1/2. Okay, so there is a difference. They use a stricter bilinear estimate, but still using Fourier restriction method. And then these two guys here, they use the Fourier restriction method, establishing some bilinear estimates. Then we can observe that the results that I already mentioned, right? They are all global if S is greater or equal than 1. Okay. Then recently, Kinoshita in 2019 obtained the best possible result for this method. And one can see that it's not the one given by the scaling, right? So he proved that this problem is local well posed, right, in 2D if S is greater than -1/4. Okay? So what he did was introduce, well, he used sharp bilinear estimates, right? And then he introduced this Loomis with inequality that is coming from harmonic analysis to study convolution, right, of several surfaces. And then he could put this in his proof and get this nice result. So in particular, he can prove local well posedness in HS S greater or equal than 0. So he can do it in L2. Then, if you move to any power greater or equal than 2, still k integer, right? So you can see that the scaling argument suggests to have this number, right, as the best possible result, the best possible index for the subwheel space to have a local solution, right? So, and that was proved by Ribot and Bento in 2012 in the case the k greater or equal than 4. Okay, so they proved that the generalized CK equation is local well posed whenever S is greater than this number for k greater or equal than 4. In 2015, Axel Grunrock proved that in the case k equal to 3, it is also possible to get to the scale, okay, S greater than 1/3, right? And in the particular case, k equal to 2, right? The Kinoshita proved that the best possible result is attained, and this is S greater or equal than 4. Okay, and so that improved what Ribot and Bento did in that situation. Okay? So still, I can say that you have global existing solutions in H1. But then recently, Bashatai, Raj, Farah, and Rudenko proved that you can do better and you have global results. In this case, the modified case for S greater than 3/4, okay? Under some restriction on the initial data. Then we can pass to the 3D, that is more physical, okay? K equal to 1, and then there is a result by Ribot and Bento, where they show that the local well posedness in HS is greater than 1. Okay, so previous result was obtained by Jean-Claude Saul and myself, right? But still above 1. And then Molinet and Pilot, they proved that this problem is local well posed for S greater than 1. Recently, last year, Herr and Kinoshita showed that this is, one can do much better, right? And then you can do Picard iteration method and obtain local well posedness for S greater than -1/2. And so you got global well posedness in HS, S greater than 0, right? And then you can see that in dimension 3, you can also work with the general powers, integer general powers, and then you got the result of Axel Grunrock in HS. Again, the scale. He proved this, the local well posedness the scale. For k equal to 2, so you obtain a local result in HS greater than 1/2. The same with Kinoshita, 2 different methods, right? And then Kinoshita proved that you can do. Yes? S greater or equal than 1. Right? Okay, so next, I would like to comment on global well posedness for the modified CK equation. In that case, we have L2, right? we have a problem with L2, and then we can have L2 it should be the greatest space that you can solve the problem, right? But then, even to prove a global solution in H1, you found the following obstacle here. So remember the mass is just L2 norm in L2, the L2 norm square, and then the energy is written in this way. Okay, so what we want to do is to find a priori estimate using these two quantities, right? So there is no problem, we have control L2, but then we would like to control derivative, right, of U, so the gradient. And so what we do usually in PDE, right, is to use the Gallardo-Nirenberg inequality, and better than that, a sharp Gallardo-Nirenberg inequality. So if you do that, you end up with this inequality here, right? And then there is something that you can see right away. So you have this power 2, and so we require that this quantity should be small, right? Should be less than 1. And then you can do that, right? So you started with initial data in H1, but L2 has to be small than the normal of this one. Q here is the solution of this stationary equation, right? Okay, so if you have this condition, then you can extend globally the solution, right? So this is the critical situation in the case in dimension 2, right? With power k equal to 2. And then, so you have starting with initial data in H1 with this condition, then you have global result. So what about if you don't respect this condition? Well, recently, Farah, Holmes, and Rudenko, and Jan proved that if you don't satisfy this condition, so the solution of the problem may blow up, okay? And they may blow up either in finite time or infinite time. And they were inspired in the work of Martel and Merle for the critical KDB, all right? So it was a long time stamp problem, very difficult, and they could solve the blow-up of solutions in the critical KDB equation, okay? So the same thing happens for the CK equation in dimension 2, right? So what we notice right away is that in the 3D case, we don't have any scales that say that L2 is a critical space, right? As in the case 3D, right? So what the question that naturally appears is, okay, what is the generalization of the CK that you have L2 as a critical space, okay? So what we do is, well, we relax instead to have a K integer, right? We can think on that as a real number, and then we do the same computation as before, and the scale give us the number that I'm gonna show now, right? So it's exactly the same equation that I wrote before, where the derivative of u to the 7/3, right? So you came out with some equation. That equation makes sense, and then you try to consider the problem of local well-postness and possibly the global well-postness for that, all right? So when we say that this is critical, it's not only because the resolution space that we expect to have a local solution is L2, but also because of the nonlinearities, right? So we saw in this previous example for the CK equation that in order to get global solution, you have to have a restriction on the side of the initial data. All right, so this is the same situation here. And also, this problem, as you saw in the previous slide, you have ground states. And then depending on the power, you can see that these ground states are stable or unstable. Okay, so we have there is a conjecture along, this is an old conjecture that said that K equals 4/3 should be unstable. Okay, so but first you have to came out with the local theory and global theory for the equation. And now we have something here, right? So this is all the fact that I just telling you motivate the interest to study the initial value problem 1, right? And the first goal here is to establish a local and global well-postness for this initial value problem. And the first obstruction that we have is that even though I showed you a lot of techniques before, right? To say that we have a smoothing effect, we have Burgers spaces, we can localize and then combine both techniques, even this new technique by Kinoshita, right? We cannot implement those techniques here. Okay, so we had to come out with some new idea. And this is what we are going to show you in a while. Okay, so the result is like this. So you have a local result, and this is a nice one because you got the existence, uniqueness, persistence, right? And then the map solution, data solution is locally linked, right? So this is just a benefit to work with the Picard iteration method, right? And then there is here in the space XST that involves several properties of the nonlinear dispersive equation in general, right? In particular for this CK equation, the smoothing effect, the Stricker estimate, maximal function estimates. And then in some moment, I'm gonna show you very fast a slide defining this space. Okay, so what happened here is that, well, we try to use the method. Okay, it's between what Ribot and Bento did and what Axel Grunbrock did for K equal to 2. Okay, so we are in the middle of these two situations, right? And then the best thing that we could do was to introduce an almost paraproduct decomposition. Okay, so for that, we have to do this little Paley decomposition, then localize, then use projections, and then came out with some almost paraproduct decomposition. And with that, we obtained this local result using Picard, right? So the point is that we use in that proof the maximal function estimate, and we have obstruction there. So we can only use S a little bit above 1, right? And then that is stop this argument, and so we need to have a new idea to keep going, right? And this is what we came out with, this almost well-postness result. That is the following. Okay, so we have a local, we have existence, uniqueness of solutions, right? And then the continuous dependence is fails, right? But still, we can have a solution that has the same regularity as the one that we have in the previous theorem, right? So we have a nice regularity, right? We have existing uniqueness, but the continuous dependence is missing. So we try to do, we have a key lemma that I'm gonna show you at least the face of the lemma. And then we can change the gradient by the Laplacian, but it's still the Duhamel integral operator is just 1/3 Holder continuous, and then we cannot do more than what we did here. Okay. So we need to go back to what we know, right? So we had to use compactness and approximation and all that stuff. Actually, we went back to what Ginevra and Bello did for some for the way equations a long time ago, and then to approximate the solutions that we are working here, right? And so we came with this lemma. So you got for initial data in HS in this range, right? So there exists a time, a unique solution. Here, intersection these spaces, all right? Okay, but no more than that, okay? And then you can establish a theorem saying that you have a solution for the problem of almost well-postness, right? In this following sense. So you get a initial data in HS in this for this index, right? And then you take, now you have a solution that is only here, right? It's just in an infinity. And then intersection, all the intersection of the previous spaces. Okay, so we just look for the regularity in this case, all right? And then this theorem still doesn't give the well-postness in the total strength, but still, as a consequence of this theorem, we got this property here, okay? So we have a solution that is unique, right? And has the same regularity as in the previous case, okay? But continuous dependence, we don't. All right. So you at this point you can complain, right? You say, well, you're battling with S between 3/4 and 1, right? And probably you can go a little bit to 2. But if you go back to the scaling, actually the space that we expect to have a solution is L2, right? But well, we're still far, right? Of that. And actually, if you go to L2, we can prove that instead of have continuous dependence, we have we ask for the map to be uniformly continuous, right? So that problem is not well posed, right? So the data solution map is not uniformly continuous if you are in L2 or below. All right. Okay, so at this point we have a solution with very nice in 3/4 1, a solution that has the same regularity as in the previous case, preserving regularity between 1 and 2. And we already know that in L2 there is no continuous dependence for the problem if we are in there. Okay, so the point is, well, you still have a solution in H1, right? But then it would be enough for that to prove global solution for this equation. And the answer is yes. Okay, so we got to work a little bit more because we had to make sense of these two quantities here, right? And what we do is just, well, we consider smooth solutions, right? And then we try to establish a priori estimate, and with this a priori estimate, we can come to enough regularity to make sense of these two quantities, okay? So now we have, for the solution that we obtain, we have a conservation of mass, we also have conservation of the energy, okay? And with these two quantities, we can hope to obtain global solution, right? And that's what we have, right? So we have the a priori estimates, right? So the conserved quantity makes sense. And then we can obtain a global solution whenever this guy is sufficiently small, right? So how small? It should be smaller than the L2 norm of the corresponding ground state, but at this point we don't know. But still, we know that it has to be small to obtain, to have a global solution of the problem. All right? And the set of results that we got in this work with João Pedro is that we finished with this observation that is, if you are interested in this problem, Carlson, so this raises question. This is almost everywhere convergence, right? So he considered the Schrödinger operators, and then the question was for which S in R we have this for almost every X, right? So he showed that this is true in H1 force, right? When N is equal to 1. Okay, that was a long time ago, and since then, the study of this problem has been gaining a lot of attention, not only the linear, but also the nonlinear, as in our case. And using a recent work of Copan, Luca, and Staffelani, right? We could prove that if you started with initial data here, right? Then we can prove that the solution that we have, right, converge almost everywhere for X in RT. All right. All right. So now I would like to tell you at least how to solve the first theorem, right? How we prove the first theorem. And then this is a little bit scary, but I'm just going to show this, this is technical, and then I would like to just to give the ideas of the stuff, right? So we have to introduce projections, right? And then we are going to take advantage of the following fact, right? So you have a literal Paley characterization of this literal Paley characterization of the solid spaces if you are in HS, if and only if this is fact. Okay, so we can traduce everything in HS, right, to this norm here. Okay, and now we are going to work with this kind of norms. Then this is also a scary slide, but it's just telling you that you have to consider the solid space where you are working, okay? The smoothing effect that this dispersive equation has, then the maximal function estimate and the Stricker's estimate. So what we are doing basically is to follow the main idea of Koenig-Ponce-Vega, right? Introducing the smoothing effects, right? But in a different framework, using projection and all that stuff. Okay, so and here we define this XS space, XT space that combine these four properties. So where we want to prove the theorem, right? The smoothing, the maximal function estimate, the Stricker's, and so on. Okay, and then this is just technical and about that. Okay, so. And so it's more important this, because this is one thing that we look for when we are studying dispersive equation, understand the structure of the linear problem, right? And if possible, to translate these properties to study the nonlinear problem. So the first thing is, well, you have this is a nice unitary group, right, associated to the solution of this problem. And you can see that you can obtain solutions that are more regular than initially, right? if you change the space. Okay, so if you started in L2, then in this space, I said this is L2 in Y. Y means Y and Z, and time. Then you have gain of one derivative, right? Of the gradient is bounded just by the L2 norm of the initial data, right? Then this is the difficult, the structure that we have in our analysis as this is sharp, right? So and the endpoint is equal to 1. This is the best that we can do it. Okay, nothing better than that. And this result was obtained by Ribot and Bento. Then the useful Stricker estimates are this one here. Okay, so again, this is you started in L2, and then the solution of the linear problem is in a better space. All right, so that's a good thing that the dispersive structure gives to us, right? And it was proved by Axel Grunrock. Then we have, so I think you know that I follow in instead to study the PDE, we are studying the integral equation associated to the PDE, right? And then we know everything about the linear problem. And then we would like to know what happens for the Duhamel part of the equation, right? And so we can see that we can translate what we know about the smoothing effects in the linear case to this integral, right? All right, so this is natural here. This is using, this is not trivial, but duality that we need to do in order to get this this gain of derivative. And then you will observe that you gain here twice the amount of the derivative that I mentioned in the first lemma for the linear equations, right? And then you have this condition for the maximal function, right, in L2. And then you see this is the best you can do it in that situation, right? And then you're losing something, okay, already. And also, at this point, we should look at these spaces, right? So this space is fine. You have L2 in Y and T, but then you have L1 in X, okay? So L1 is not always a nice guy, right? And then we had to get out of L1 somehow in some point, all right? Okay, so besides that, we did this Stricker estimates in this framework, like that, right? And so to do that, we have to follow what these three guys did, Bao-Jian, Ligia, and Julian. This is an isotropic version of the Chris-Kessler lemma, right, for the target estimates, and then we can implement that for our problem. Right? Okay. So next, what we do is we want to prove the problem. Okay, we want to prove the local well-postness using contraction mapping principle, as I mentioned in the middle, at the top. And then what you consider is this equation here, right? So this is an integral equation. You consider a ball, so you're looking for some time 1A positive, right? That makes this guy be contraction in this space, all right? And so this first part is okay because I showed you before that you have all the linear estimates that are nice, and then this is true, no problem for any S. Okay, here there is probably S greater than 1, then 3/4 is okay. All right, but then we need to study the integral part, right? And to do that, well, you have two possibilities. The previous propositions, right? I want to show you. We end up always in the same spaces, right? Previous. Okay, so all the estimate that we have for the linear equation, right? For this Duhamel part, right? End up here. So same with this, okay? So we can go and do the estimates in this, right? In this part. So if you do this, it's just to prove that the operator that we have defined before, this one here, right, is well defined, or you can use this to prove the contraction, right? All right, so this is, so if we do this, the estimate that we need for this is okay for this, just making b equal to 0. All right. So what is the point? The point is that if you take any of the estimate, any of the norms that we introduced to study the problem, everything finish if we do the localization and the projection in these spaces. Okay, so you have L1 in X, L2 in Y and T in these small blocks, right? And then you have to add together the whole thing. Okay, so what was the idea of Ribot and Bento? Ribot and Bento, when they consider the Sakharov-Kuznetsov equation as k equal to 1 in 3 dimensions, they have this very nice identity. Okay, so they could write this in this decomposition, right? So this is very nice. This is a very neat formula, but then we don't have that. Okay, but then what we did was to look for something similar to this, or inspired with this. So this is the nonlinear lemma that I mentioned several times in the. I should mention, but sometimes I didn't mention that this is going to give the results, right? So this is very technical stuff here, right? And then you have to do, this is, John Pedro is a harmonic analyst and he enjoyed very much doing this, right? So he made this computation very carefully and we came up with this inequality here. And the whole point of that is the following, right? So we need to write this in some way that we can have, right? And so you do some projections first, right? And then you use also the mean value theorem for integrals, right? To get something very clean. Oh, clean for us, right? So this is the whole point of the proof of this part. Okay, so proving local well-postedness using contraction mapping principle involve this almost pseudo-parametric identity, right? Once you have that, of course, this is a long way, just jumping, just telling you what is needed, right? But then once you got that, then everything is easy. You got this operator, right? You can choose the A that I said that we were looking for before, a time that should be like this, and then we can have a local result, right? Here for S between 3, 4, and 1, using, and then we have the contraction, the map data solution is glitches instead of being just continuous. All right. So this is roughly the proof of the local well-postedness for this problem. Okay, so this is the idea in many of the arguments to show the local well-postedness for several nonlinear dispersive equation. Okay. So next, I'm gonna summarize the problem that we left, right? Open, right? So we need to well, now it's open. Anyone can try it, and then you have the following things to do, right? So you need to have a strong resolve in Sobolev spaces within this s greater or equal than 1. We also would like to have a local result that is sharp, right? So we have two problems that we study in nonlinear dispersive equation, right? Then when you get the global result, once you have the local result in a strong local result in H1, then you need to show that in fact the global well postnet comes as before, right? As for initial data in H1 with a small data in L2, that depending on the size of the ground state. And if you got that, then there's a wonderful problem to show that for large initial data, inspired, for instance, in Martel-Mer or Koenig-Mer works, solution may blow up, right? And then if you have that, you can talk about the dynamics of the blow. That is also our standing problem, right? So, of course, in this problem, we have this constraint about the global results, right? And then, but if you don't have any constraint for the global results, you don't have a blow. So you can go to the conference of Claudio, and Claudio is going to tell us the dynamics of the global solutions, the behavior of global solution for some nonlinear dispersive equation. Okay, so I'm going to close here, and thank you very much for your attention.
Thank you, Felipe, for your very interesting and informative talk. Following the format of the meeting, we are going to move from Rio to Santiago in 2 minutes. And we are going to have Claudio, and we'll have to ask Claudio to connect. Well, it's my pleasure to introduce our second speaker, Claudio Muñoz, a very young, famous analyst, PhD from 2010, moving from France to Santiago, who will be talking about long-time asymptotic for large data in some dispersive models.
Thank you, Gustavo, for the nice presentation. I'm very happy to be part of this meeting. I'm very sorry I was with the kids, and it took me some time to finish, right? So today I will talk about some recent work with several people. And once again, I thank the organizer for the invitation. And I also thank the people that my collaborators that are part of these works. So so I think I will go ahead. I will talk about the long-time asymptotics of large data in some dispersive models. Okay, so I will try to explain you, try to make the presentation not so technical in order to all the people in the audience be able to understand at some extent. So the first thing I'm going to talk about is about the so-called generalized KDV equation. For those of you who doesn't know the equation, I will try to explain you here what is the equation, or what are the equations we work with, and essentially what the problem what is the problem we are interested in. Okay, so there is a one-dimensional equation, the KdV equation, which is just, I mean, it's very simple to write down. It's the time derivative of a function u, which is a scalar. It depends only on the time scale and space, so it's real valued. And the time derivative is related to the third derivative of the function u and the derivative of a nonlinearity. And that's the so-called generalized KdV equation. For the purposes of this talk, I will only mention 3 cases: the case where p equals 2, 3, and 4, and no more than that. I mean, and when p equals 2, this is the famous KdV equation. It is a well-known dispersive model, one of the probably 3 more important dispersive models in the community. And one of the nice things is that if the power is below 5, then if you put initial data in H1, then the equation is globally well posed. So in some sense, it represents in a good way the physics. Okay. So more importantly is the fact that when p equals 2 and 3, when p is 3 is the so-called modified KdV equation, the model is integrable. In some sense, it has plenty, huge amount of hidden algebra and structure that makes the equations in some sense easy to solve. I'm not saying that it's easy, but I'm saying that this structure is very useful to fully understand the equation, at least in some particular spaces. Why we consider only the case p below 4? It's because when p equals 5, you know already that some complications appear. In particular, you may have blow up, right? That is actually true for the power p equals 5, and actually it's also true for powers bigger than 5, but not every power. Okay, not every power, but it is still an open problem in the field to fully understand the geometry of solutions when p is bigger than 5. And if you consider, so the key question for us is to understand the asymptotics of a large globally defined solution in the non-integrable case. As I told you before, if the equation is integrable, then you can say a lot more. But if the equation is not integrable, for instance, if the power is 4, then we may say that I mean, in terms of asymptotics of solutions, we don't know too much. Okay, so that is an important question that I like to work. And in order to explain you why it's interesting, first I will mention what is a soliton. A soliton is a solution of the same JKdV equation, which has this form QC of the variable x minus ct, right? And c is the speed. It's a positive quantity, and it's a fixed profile QC. So QC is in the energy space H1, and it solves this ODE. So it is a standard solution that is exponentially decreasing according to very sticky Lyons or I mean. So a soliton is a sort of fixed profile that moves to the right because C is positive, and it's an exact solution of the equation. An important open question in the field is the so-called soliton resolution conjecture that states, roughly speaking, that except for some very particular cases that are also important, a globally defined solution to JKDB should decompose as time tends to infinity as the sum of solitons, I mean several solitons at the same time, not only one, but several one, and some radiation. And by radiation, I mean linear behavior, right? So the equation is non-linear, but if you raise this power here, you get the linear equation that is called the Airy equation. And of course, this statement is very, very naive, very weak in some sense. And in order to make it rigorous, essentially you have to go little by little, step by step, and case by case. So it is not something that is clear to state starting from scratch. Except for some integrable cases, I should mention here the work by Shen and Liu in 2020 for the case of the MKDB paper, MKDB equation. This conjecture is far from being established in the non-integral setting. Even in the Shen and Liu paper, they make some assumptions, right? They make some assumptions, but they obtain the so-called soliton resolution. And there are plenty of other papers in the integrability community, but I will not mention them here because of time reasons. But of course, if you want to learn more about this, you can start out reading this paper and then checking the references. I think it's a very good way to know the literature. And about JKDB in a general setting, in a general situation, I recommend the book by Linares and Ponce that is very self-contained, and it's a very good introduction to the field, in particular the JKDB cases. So in 2017, with Gustavo, we met in Canada in a congress. I don't remember exactly the name of the congress. And we discussed a way to say something about the long-time dynamics of solution to JKDB, but under essentially no assumption at all. I mean, large data, very weak regularity, and that's all that stuff. I didn't mention before, but in the remarks, you will probably have a more complete description of the field. Essentially, I think that except in the integrable case, there are no descriptions of solutions for large data. Okay. So with Gustavo, we considered only KDB because at that time only worked for KDB, the proof. So P equals 2. So remember that the equation is integral. So in some sense, it's something that maybe people know. And we assume that we have a solution in the standard H1 Sobolev space, as Kenneth and Ponce Vega proved some years ago. But additionally, I put here in red a condition that is somehow strange, maybe, that the solution should be bounded in time in the space L1, in a space. So then if you have a solution satisfying this condition, no restriction on size, then the L2 norm of the solution should be converged to 0 in the region essentially bounded by the power T1/2 as time tends to infinity. So you have a strip of size T1/2 that grows to infinity. Of course, if you have a T1/2, you will not enclose solitons, because soliton, they travel to speed T, or speed 1 if you wish. So this result is not in contradiction with the fact that the equation has solitons, but says a lot about the region where solitons are not present. So this condition is not empty. Fortunately, solitons, they satisfy this condition. There is no restriction on the size of the data. We don't use integrability techniques. It's just what I will not have time to explain you the techniques, but we use virial identities that have been very useful to prove long-time behavior in the past year by many people, starting maybe by in the 80s, right? And our result is not valid for p equals 3 because essentially when p equals 3, the result is false. This cannot be true because there are some solutions that are called breathers that are oscillatory in time, they don't decay, and they are localized in L2. Okay, so they are periodic solution, periodic in time. And that means that this cannot be true. Okay, and for p equals 4, we had some problems and we couldn't say anything about that case. So by that time, we had this result by Efrin Kochtataru, where they gave a much better description, more detailed description of the asymptotics in the case where you have a small solutions. But the description only works up to some time. If the size of the data is epsilon, then the time where your description works is of order 1 over epsilon to the power 3. On the contrary, this result works for all time. So with Gustavo, we continued working on the Benjamin-Ono equation, which is another very prestigious dispersive equation, very hard from the Fourier point of view, and it is also integrable, right? But the description of the integrable setting is very hard and still incomplete, very incomplete, I think. So everything that can be said here is relevant, right? It's important. And because of this here is a Hilbert transform, it's a non-local operator that makes the equation harder because there are no smoothing or, I mean, there are smoothing estimates for sure, but they are very weak. And in the Fourier side, the Hilbert transform is just represented by this symbol, right? It's just a Fourier transform of an L infinity operator. So it gives no regularity at all in some sense. So here we proved the following. In some sense, it was harder than KDB, and we have to assume more and prove less. Okay, but we assume a solution that was defined in the energy space H12. That's the energy space for Benjamin-Ono. Actually, the solution is defined in L2, if you wish, and that's a result of Ionescu and Koenig. But for our purposes, we needed H1/2. And we also assume we weakened the L infinity condition, only assume an L infinity log, right? And in order to get this condition here, we had to assume some growing of the L1 norm in time, right? So the L infinity norm in time of the L1 norm should be bounded by a power of the time. That power should be no more than 1/2, okay? So under this condition, then we can say that the limit of the solution, the L2 norm and the L2 norm of the gradient in a certain neighborhood is converging to zero, the limit, okay? And the size of this neighborhood is depending on some parameters. Actually, you can play a game with the parameters depending on the A that you have here, the B you have here. They are related by this condition. So in some sense, the bigger the A, the smaller the B. Okay, so that's the trick to be played. Okay, so at this point we realized that that this power here, T1/2, was something that was not sharp at all. Okay, because actually you could move so the power here, of course, not going further than 1/2, but in some sense you can play a role, a game. I mean, you assume that your solution has some growth in time of the L1 norm, then you can say something about the infinity, the decay of the solution in a certain neighborhood, and that neighborhood depends strongly on the rate of growth. So I think that my computer is running out of battery, but I still have 10%. So I will go up to 5%. Can you hear me right?
Yes.
Okay, thank you. So there are more applications. Actually, this is not difficult to apply to other dispersive models like BBM, Kamasa-Holm, and very recently in a model called the intermediate long wave equation, which is also a very, very important equation from the physical point of view. So very recently, every step is, I mean, just an improvement of the previous one. We did something we couldn't do better, and then we started thinking, I mean, some time, and after some time realized another thing. So last past year, with Mendes and Poblete and Pozo, we improved the result of Ponce and myself in the following sense. It is something like we improve something, but on the other side, we lose something. Okay, so forget this set here for the moment. I just will mention that we assume that the data is only in L2. Okay, so, and we still work with KDB. Okay, the data is in L2, and then we know that the limit of the L2 norm of the solution is converging to 0 in this region. Okay, this region, if you forget the t to the power n for a moment, this will be modulo of x bounded by a power of t. The power of t can be no more than 2/3. Okay, so that's the largest possible size of the window, where you know at least that for one sequence you are converging to 0. Okay, and if you want to go further than 2/3 in the power here, what you need to do is to move the window, right? You move the window in a certain power t to the power n. Okay, you move the window, and n can be made as large as, I mean, it can be near 1, can be almost 1. If you choose B small enough. So if you move further up to power t, then the size of the window has to be smaller. Okay. So if you are near the soliton, the solitons are at power t to the power 1, right? If you are near the solitons, just behind them, then the size of your window has to be of order 1. It cannot be larger than that. But it says something. It says that at least if you translate this result into L infinity norm, then it says that at least the L infinity norm of the solution is converging to 0 at least for a sequence. So some remarks, this result is still valid for non-integrable perturbations of KDB. I mean, it is not related to the integrability of the equation. It also works for the power 4, but we need data in H1. I mean, it is not so simple as in KDB. And that makes the things interesting, because if we can translate our result to a non-integrable setting, it should be quite interesting. And it turns out that you can follow Ephraim Cox-Tataru's paper. They do some sharp area decay estimates. I mean, they have linear behavior and they improve some decay on the linear behavior. If you confront it with these numbers, they coincide, right? They are the same, okay? You cannot go further than 2/3, okay? Otherwise, this limit should be positive, okay? Okay, so as I told you before, obtaining the lim sub property is an open question still now, even in the small data case. But I should say that it is not something that is strange. Actually, there is a recent result by Ducaers, Koenig, Xie, and Merle from 2017, where they prove much more than us. Okay, the full soliton conjecture resolution in the case of the focusing energy critical wave equation, but along a sequence of times. Okay, so in some senses, it is something that is one step that is necessary for the proofs. And we apply this result to several other models. I will mention only 2, and in the remaining time, the Sakharov-Kuznetsov equation, which is here. Okay, it's a 2- and 3-dimensional generalization of KDB given by this Laplacian here. And at the beginning, it was not easy to get a result, because in 2- and 3-dimension things are more complicated. But at the end, we end up finding a way to prove a result, right? We still assume data in L2, no more than that. Then the limit of the L2 normal the solution converges to 0 in this region drawn here. Okay, it's a sort of a rectangle that is growing with time. In the y variable grows this way, and in the x variable grows this way. The t to the power b, and b is a number that is between 0 and another number that depends on a parameter r. That is just a parametrization of our geometry, and the number r has to be bigger than 1/3 and less than 3. Okay, so Gustavo, how much time do I have?
Well, you started later. I think that you should take at least 4 more minutes.
Okay, give me 1 minute to find my connector, please. Okay. Okay. So, you know, in 1 dimension, the geometry is easy. In several dimensions, the geometry is more complicated, right? Here is simple. It's just a rectangle. But in another example I will mention later, it will be also a little bit complicated. About the lim sub problem, here we have a very recent result with Gustavo that is still under preparation. So take any global solution to any subcritical JKDB equation. So power P equals 2 and 4. No, any power 2, 3, and 4. Okay, it doesn't matter the power. in the energy space, then the limit of the solution when t tends to infinity in L2 is converging to 0. And what is this region omega? This region omega is the union of two addition regions. The region very, very on the left, I mean, farther than t on the left, and starting from t on the right. But this number C not here is a number that depends on the size of the initial data. Okay, because we may have solitons and we need to get rid of solitons. So this C naught is important in that sense. But it's a full limit. We know that every possible solution of the equation should converge to 0 in these two regions. Okay, at least on that size of the domain, we know what happened. And on near 0, we have the limit only, but it is relevant for the whole knowledge of the picture to know the opposite size. So here I will mention an example, very quick. The KP equation in R2, which is written here. It's an equation that is also a generalization of KDV, and it has a non-local term, right? And this non-local term, it mixes some transfer effects for waves in the Y variable. And essentially has two cases, k equals -1, kappa equals -1 and kappa equals 1. Kappa equals -1 is called KP1 and kappa equals 1 is called KP2. And this non-local operator essentially in the physical literature is defined this way. And it's an equation coming from the physics, okay, from the 70s. It has rigorously obtained by Lane and Lanesso some years ago. And for this equation, we have a beautiful geometry, but I will not talk about this because I just have some, I'm sorry. So we have beautiful geometries because in one case, in KP1, we may have what is called LAMP, a sort of soliton solution. But the soliton solution can be extended to 2 dimensions here in both models, KP1 and KP2. Okay, so the geometry is much more richer than in the KDB case, and that makes things more complicated. Okay, but here what we did was the following. So just to mention, in this region here, in this square here, we proved that the limit of the solution has to converge to 0, okay? Here you may have objects like lamps and solitons. So this is a forbidden region for decay. We also proved that in this region Y bigger than T, the solution is converging to 0, but not in a band. I mean the full half plane Y bigger than T is converging to 0, and this part is also X bigger than T is also converging to 0. This one also, and more importantly, this half plane can be in some sense shifted on or turned into some angles, right? In an oblique way, they can be oblique, and even in that case, we also have decay. Okay, so it's not something related to a rectangle geometry, but a more complex geometry. I mean, with some angles and all that stuff. So it is still a work under progress, but we have some preprint, right? First preprint, but we expect to have some news in the following months. So here is the theorem. It is written in a mathematical way. This is a joint work with with Mendes, Poblete, and Pozo. And in the first region, the interior region, we have limb, but in the full exterior regions, we have a decay to zero, full decay. Okay, so that's all I wanted to say. Many thanks.
Thank you very much, Claudio, for such an interesting talk. And following the format of the meeting, we have some time for questions. And okay, I think that we should unmute everyone. I don't know how to do that.
No participant can.
How can we unmute all to see if people have questions to Claudio and Felipe?
You can just raise your hand.
Okay, you will have to raise your hands, and you will be unmute.
Or directly unmute. They can do that now.
Okay. Okay, Jaime is clap, but he's not raising his hand.
Could you please, Claudio, stop sharing your screen?
Okay.
Okay, let's see if we get any question. Well, I have a question for Claudio, since there's other questions. When people talk about the resolution conjecture, how do you adapt the existence of breather there?
Well, you have to add breathers. I mean, not only soliton, but also breathers. So,
okay.
But they adapt very well. In some sense, they cannot travel faster than a soliton. I mean, they can, yeah, in some sense, there are some sort of decoupling between breathers, solitons, and radiation. It is not a simple decoupling, but at some point you can realize that they have some decouple dynamics.
But can you have I'm sorry, another question. Can you have a double breather?
Sure.
Okay.
For sure. I know that someone wrote a paper about breathers very recently, constructing multi-breathers. They can also be found using integrable techniques. But finding those solutions in non-integrable models is something very difficult.
Okay. Any other question? No. We were waiting for more questions. We have still some time.
Okay.
Well, if there is no question, we will send both speakers, Felipe Linares and Claudio Muñoz, for the wonderful talks. And we move to the next step in the format of the meeting.
Thank you.
Okay.